Okay, so yesterday we stopped at the introduction to Bayesian inference. Or Bayesian estimation. We went through the process of defining a Bayesian model, which basically is the same as a regular model, just involves defining some prior distributions on the population parameters. We briefly mentioned that with Bayesian estimation, we are trying to estimate the posterior distribution. This is as opposed to just getting a point estimate for the population parameters. And so I'll touch upon that a little bit again, in case some people here might not be familiar with these concepts. But then hopefully after that, I will show you some more like how after you've done a fit or an MCMC estimation, how do you validate it or make sure that it converged, or at least detect lack of convergence? What are the diagnostic plots that you need to look into? And then also show you how you can use then the output of this fit to do counterfactual simulations and trying different doses and so on. And then after that, once we're done with the whole warfarin case study, we have another case study on tumor growth dynamics and survival modeling, which we will sort of cover together almost. This is going to be one case study. And then at the end, if we have time, I also intend to walk you through some very introductory material to DeepPumas, which is our machine learning or augmented machine learning into nonlinear mixed effects modeling solution. But beside the software itself, I think there are lots of good ideas that can be learned, and yeah, there's a lot of interesting research going on right now in our DeepPumas group that goes way beyond just the software tool itself that we are developing. So that could also be interesting. And as I said last time, we do have a more dedicated workshop to DeepPumas, machine learning, and AI for drug development that's happening in Basel, Switzerland, in this upcoming April. And so if you're interested, you can go to our events page and you can find more about that over there. Yeah, if you're even more interested, you can actually sign up and I'll be able to see you there. So Nicholas Korsbo, my colleague and one of the main developers of DeepPumas and basically the person who started DeepPumas at Pumas AI, and myself will be teaching that. So yeah, looking forward to seeing some of you hopefully there.
Short question. This is Marian from Berlin. I just wonder if we can make sure to have like a sometime on DeepPumas. I think last time you mentioned that we could decide if we reduce a bit of the survival modeling, tumor growth dynamics modeling part to make sure that we touch upon DeepPumas. I mean, if you can make a poll or so, we can also do it here. I don't want to speak for everyone in the room, but I think at least to me, it would be interesting to get some exposure.
Sure, let's do a quick manual poll. Can I see some thumbs up if people want to switch DeepPumas and survival modeling? Okay, I think almost half the room, maybe over half the room now, almost. Some people maybe did a thumbs up twice, but no, I think almost half the room wants it. So yeah, so let's do that. The rest of the people, I'm assuming. Actually, let me ask the same question, but in reverse. Anybody doesn't want to switch the two? Okay, so I guess the rest of the people are either neutral or not listening. So either way, we could try switching things around.
Okay, thank you.
Awesome. So okay, so then let's finish the warfarin example or case study, and then I don't have a lot of material prepared for the DeepPumas, but I do have so we've given a DeepPumas workshop in the last ACOP essentially, and the material for that is also public. And so my intention was to walk through some tutorials. We also have some tutorials about DeepPumas. And so maybe I'll walk you through some of this material. It's not going to be the most, let's say, organized, pre-planned material, but I'll try my best to walk you through some of the content that we have for the DeepPumas workshop. But yeah, we'll see how that goes. At the end, I would still maybe like to cover a little bit tumor growth dynamics and survival modeling, but if no one here is interested, then I'm also happy to skip that. Yeah. let's do that. But let's first wrap up the other material that we started. And so let's go back here. Actually, before I do that, I had a few announcements as well that I wanted to make. So yesterday I was mentioning the how to set the number of threads on the Pumas desktop. I thought I might have given people the wrong impression that on Julia Hub you also need to do this. You don't. On Julia Hub we automatically set the number of threads to the good number of threads based on the machine configuration that you picked. And so this is only for the desktop version and only for now, and we hope that in the future we can fix this. But you can always double check by going to the settings and seeing the number of threads, or by literally just calling threads.nthreads. So if you call threads.nthreads inside Julia, you can always confirm how many threads are actually running. And so you can call this and double check for the next release as well. So with these announcements out of the way, let's go back here and try to wrap this case study up. And let me just quickly recap what we did in the Bayesian part. So yesterday we discussed how to define prior distributions here. And that first thing you probably need to do is to make sure the support of the distribution matches the domain of the parameter. And that if the parameter is positive, you want your distribution to have positive support. If it's unbounded, you want your distribution to also have unbounded support. And if it's a matrix, you want the matrix support distribution, etc. And then the next thing you probably want to do is think about the center of the distribution, if you have any reasonable values to use as the center of this prior, and then the spread or the dispersion parameters of the distribution, how dispersed or how confident or non-confident, I suppose, or not very confident you would like to be in that prior distribution choice. And once you do that, now the goal is with Bayesian, is to take this prior distribution and then take the data that we have, which we have in our population, but we have the observations defined here in this model. But essentially take the model, take the prior distributions and the data, and then try to figure out which values of parameters, so which values of pop CL, which values of pop underscore V, etc., all the population parameters that would be plausible values to have potentially generated this data. And so it tries to give you all these different possible values that may have generated this data, given your prior belief about all the plausible values for this parameter and given the observations that you've had. And so it updates this prior belief, which is represented by this distribution here. And then it tries to give you a set of samples, essentially, a set of values for all these parameters that may explain your data well, given the observations that you have. And so that's sort of the idea. And then this set of samples are called posterior samples, and the distribution of the parameters after having observed the data. So after you look at the data, your posterior belief essentially is described by this posterior distribution, and the posterior distribution often is not very tractable or not easy to sample from, and so that's why we use MCMC or Markov chain Monte Carlo. Just a brief sort of overview of why we're doing this, but because you also get a distribution at the end, this is why this is comparable to, let's say, a combination of a fit and a bootstrap in regular empirical Bayes frameworks, and so this will automatically give you the uncertainty in the parameters, and you don't need to do any bootstrap after that, and so that's sort of the nice advantage of that. And it also generally makes less assumptions about your model than many of these other methods that are commonly used for uncertainty quantification. But also a slight point or a nuanced point that's worth mentioning is that we're actually sampling not just the posterior of the population parameters, but the joint posterior of the population parameters and the random effects here for each subject. And so we're sampling the joint posterior of all of these. And so we have let's say we have 10 subjects, then we have a PK underscore eta and PD underscore eta for each subject. And so we're sampling 10 PK underscore etas, 10 PD underscore etas, and all of the population parameters simultaneously in the MCMC estimation. We also have an algorithm that can marginalize this with FOCE, for example, or Laplace, and then only sample the population parameters here, which can sometimes work better in some simple cases, but we found that it doesn't always work better. But in some cases, it does give you a pretty good speedup to do that. Okay, so with that sort of theory out of the way, this is the syntax for doing Bayesian estimation. And so once again, we just call the same fit function. The first argument is going to be the model, and the second argument is the data or the population. The third argument is a name tuple. That's the initial parameter estimates. And so we have these initial parameter estimates here, which are given by this init_params function. And it tries to use the distributions that you defined and get some reasonable measure of the or reasonable initial estimates. Now, if you want to randomly sample new estimates every time, then you can also call this sample params, which you might want for some other purposes. But we also have the sample params that allows you to sample from the prior distributions. And internally, then we sample 4 chains, MCMC chains, and we sample, you can pass the number of samples you would like to use in this chain. And so the number of samples here is comparable to the number of bootstrap samples, for example, that you would like at the end. And the only difference is that there is actually an adaptation phase in the algorithm that we use here. And so the adaptation phase we generally discard these samples at the end of a fit as sort of warm-up samples. And so the adaptation phase is used to adapt some of the algorithm parameters. So this algorithm that we're using, the no-U-turn sampler, has a lot of these hyperparameters that get self-tuned over time as you use the algorithm, and they only get adapted or tuned by during this 100 adaptation steps that we have at the beginning. Or however many you want to use. For some reason, it's common to use 50% of the samples for adaptation. You can use 25% if you want, but making this too small can actually negatively hurt your convergence at the end. And so you want to have this sufficiently large so that you actually learn good hyperparameters, because a good algorithm will generally converge faster than a bad algorithm or a badly tuned algorithm. Okay, and then 4 chains means we're actually running this sampling 4 times in parallel to each other. Every time you're getting different samples. And so the idea is you want to make sure that your sampling is not sensitive to your initialization or to where exactly in the parameter space you are. And so you want to make sure that all of your chains converged. And generally speaking, you expect the distributions of all the chains to be similar at the end if your algorithm converged. In some very rare cases, you might find if you use like 100 chains or something, which is generally not required, you might find 1 chain or something that might not be matching everything else. For example, it might be getting stuck somewhere, but in general, we expect that all of the chains should have matching distributions. And we're going to see some of the diagnostic plots that we can look at. This here is optional. We don't really need this argument here or this keyword argument in a real fit, but in this case, just to make it a little bit faster to run, I'm sort of limiting the algorithm parameter to a max depth of 3. This hyperparameter of the algorithm, which makes it a lot faster to run in general, but also makes it less likely to converge to the true posterior. And so you want to make sure that you don't limit this. The default value is actually 10 for this one, but I just set it to 3. And I mentioned that sometimes when you're doing Bayesian estimation, you have stiff differential equations or some parameter values that were explored may be slightly crazy or wild, and they may lead to some very implausible dynamics. But even for those parameter values, you still need to simulate, unfortunately, to figure out whether or not they lead to implausible dynamics. So because you only find that out at the end of a simulation. And so for those parameter values to be able to be simulated, you often, or robustly simulated, you often need a good ODE solver. And in general, you can also drop this parameter here. But if you see a lot of numerical errors, then you can try this one and see if that helps. In this particular case, it did help. And so this is generally useful. But I'm going to make this back to 200 and 100, and then I'll call the fit function. And now let's take a look at the output that's coming out of the fit function. So here it is checking the initial parameter values, and then it's checking it 4 times for the 4 chains. It's randomly sampling these parameter values, and then it's checking the log likelihood. And And then it starts sampling. And so if you look at the sampling here, it's showing you the number of completed chains, how many iterations in each chain. So this is just some chains are still on iteration 1, some chains are on iteration 6. And this is the total time elapsed so far, which would include the compile time. Number of steps is a function of your tree, the max tree here, or max depth tree. So generally, it's going to be 2 to the power of max depth 3 minus 1. So 2 to the power of 3 is 8 minus 1 or less. So the maximum value for this is 2 to the power of max depth minus 1. And this will be, we expect this to be small, basically, as small as possible. But because for this model, this one needed to be large, that's why I had to limit the tree depth here, just to artificially make it small for now, to make it run faster. And then here it will tell you whether or not the chains are accepting the steps, or if they're rejecting it due to numerical errors, for example. And so generally, if you see 4 trues, that means your sampling is going well. This is acceptance rates. And so you'll see that the acceptance rates should generally be close to 0.8, because that's the default value that we are trying to tune the algorithm to. So you'll see here, it's still trying to tune the algorithm, it's still trying to tune the hyperparameters, and so it hasn't actually properly converged to a good acceptance rate here. But again, that's because we're using a very artificial example with a few samples and a small max depth. And what we see here is the log density values. And so this is similar to your objective function value, but it's like the negative of your objective function value. So you want to make sure that this is high, generally speaking, and it gives you an idea of how probable your current values are, your current parameter values are. So as it's sampling, it's basically jumping from one sample to another, and this is giving you an idea of what kind of values of log density you're getting. And generally speaking, if this is still increasing, like if this is monotonically increasing or just overall increasing with time, then it hasn't converged yet to a good sort of like the parameter space where all the probability mass is, for example, or the main probability mass of the posterior. It hasn't yet reached that part. And so you want to take a look at this and how it's changing over time. But if it's reasonably stable as an interval, then it's probably reached the probability mass, or where most of the probability mass is, and it's basically just jumping around to sample from the posterior, as opposed to sort of having this optimization-like behavior where it's still moving from the low probability mass areas to the high probability mass areas. So I'll talk more about all of this in the paper as well. But you want to also probably keep an eye on this as the sampling is happening. Hamiltonian energy, again, gives you similar information, probably not too relevant here. The tree depth is the parameter I was talking about. Again, this is similar to this. So this will be 2 to the power of max depth or tree depth minus 1. Numerical errors is if any of the chains are producing numerical errors, so 4 false, that means all chains are not giving you numerical errors, which is good. And then the step size is the adapted step size. So this is one of the hyperparameters that the algorithm tries to fine tune. And so here it tells you that the step sizes are ranging from this small step to this large step for the 4 different chains. And whether or not this is adapt is whether or not the chains are in the adaptation phase. So because we're still not 50%, like the maximum number of iterations is still 36 here, and we have 100 iterations for adaptation, we're still in the adaptation phase. And so the hyperparameters, which includes the acceptance rate is not a hyperparameter, but it's sort of a result of that. But things like the step size and the mass matrix are being adapted as we're speaking. And the mass matrix is is used to essentially give you some sort of estimation or approximation of the precision of the posterior, or the covariance of the posterior. And so the ideal, ideally you want the mass matrix to match closely with the covariance of the posterior, or the inverse of it. I can't remember. I always confused. But you would like the mass matrix to give you some approximation of, let's say, the covariance of the posterior. And so often we use a diagonal approximation here, because we have a lot of these, a lot of subjects, for example. If we have a lot of subjects, then using a dense mass matrix can be less efficient. But if you have a few subjects, you can also explore with using dense mass matrices here. Or if you're doing the other algorithm I mentioned earlier, which is that we marginalize the random effects first with things like FOCE or Laplace, and then we only sample from the posterior of the population parameters using the marginal likelihood instead of the conditional likelihood in the log density, then in this case, you can also use a dense mass matrix. And I think it uses it by default, actually, because, again, the number of parameters in this case will not scale with the number of subjects. And so it should be safe to use a dense mass matrix. But again, much more details and even intuition about this are provided in the paper, the Bayesian workflow paper that I mentioned yesterday.
Maybe one short question. So you had the n-adapt parameter. Is this the same as the warm-up samples or burn-ins in STAN, for example, or is there a difference now that we specified here?
In general, so they're not the same thing in that the adaptation steps are just referring to the number of steps that the algorithm is going to adapt its hyperparameters. Now, it could be that at some point the algorithm stopped adapting its hyperparameters in the sense that it converged to good hyperparameters. It doesn't need to adapt it any further. And so technically, you don't have to throw away all of the adaptation steps as warm-up. But it is a sort of common practice too. And so it is a common practice to then go ahead and discard all of these adaptation steps. But keeping in mind that some of these adaptation steps might also be usable. So it's not necessarily like the two concepts are not the same thing. They're two separate concepts. You could also end up with a case where you throw away all of the adaptation steps, but your sampler is still not converged to or like is still moving towards the high probability mass areas. And so technically you can still get valid samples, but you might still need to truncate a bit more. And so I would say the official answer is no, they're not the same thing, but the common practice is yes, they are the same thing. And just
okay,
like
because I just
whatever.
remembered that STAN kind of I think the default option is that you just specify the warm-up samples and the actual samples. I'm not sure if the default option in CMD STAN is then to just set n-adapt to the number of burn-ins, or if you can specify that at all. I was just confused if you just have a different name here, or if there's just a default option in STAN, for example, that they set it to equal values.
Yeah, I believe even in STAN, you can actually take a look at the adaptation steps as well afterwards. But I think by default, it might be discarding it. Yes. But yeah, don't take my word for it. I'm not
Okay,
a STAN expert.
Yeah. No worries. Thanks.
No worries. But in Pumas, we actually give you all of the samples at the end, and then you can discard it explicitly here. The reason is that it's easy to discard it, and sometimes you may want to look at those adaptation steps just for diagnostic purposes. And so, and once you discard them, you can't get them back. So we thought we can just leave them, and then people can discard it manually. And you can decide how many you want to discard here. But by default, you can probably discard the same number. Yeah, this is going to take some time. As I said, Bayesian tends to be on the slower side. However, if you compare this to Bootstrap did take a long time yesterday as well, and it was only like 5 samples, and here it's actually doing 200 samples. And so it's the real question, is it faster or slower than a Bootstrap, not whether or not it's faster or slower than a regular fit, I think. And so we're going to give it a few minutes, but meanwhile, I can take some questions. Maybe I should have started the fit before explaining everything. But the good news is that sometimes this actually ETA, or estimated time of arrival, is not always accurate, and that after the adaptation phase is finished, sampling tends to go a lot faster. And so we'll hopefully observe some of that here, that after we hit the 100 mark, sampling should be proceeding faster. Also notice the log density has increased significantly from the beginning, which was minus 1,400 or 500 here. And now it's significantly higher. And so it looks like the adaptation was somewhat successful at finding these high density values, probability density values in the posterior space or in the parameter space.
Maybe I would have one further question, like just out of your experience. Apparently, you tried out a lot, of course, in the building of these MCMC algorithms in Julia and Pumas. What's your experience like when you have, like, let's say, a model which converges with FOCI or Laplacian or so? How easy is it then to switch to Bayesian? Just know that it's not always so easy that you have an actual converging Bayesian model, even if it was stable under FOCI, etc. Do you have any experience there when you try to kind of take a converged model to translate it to the Bayesian world, or?
Yeah, and it's not always a positive experience. It's Bayesian is unfortunately, I mean, even though it's more rigorous technically and like I always recommend it from a theoretical point of view, but sometimes it's not very tractable, and sometimes it can take computationally. I mean, and what takes maybe a couple of hours with FOCE, like if it already takes a couple of hours with FOCE, I would be very reluctant to use Bayesian with it because it might take a few days with Bayesian, and so it's one of those tools that I would always only use, or I would mostly use when the model is sufficiently quick. And so if I have a lot of heavy dynamics and I need to run let's say FOC itself takes like maybe hours to finish, and I have thousands of subjects, then I'll probably not use Bayesian for that. But if I have maybe like if one of those is not there, so if I have only a few subjects, even if I have complicated dynamics, then I might still reach out for Bayesian. If I have many subjects but simple dynamics, even like a linear ODE or something like that, then Bayesian can still work pretty well. And yeah, and if the fit doesn't take that long in general, like, but that's the fit taking long is usually a function of the number of subjects and how complicated your dynamics are. So I don't have a clear answer, but the nice thing about Pumas, I suppose, is you can give it a shot and see, and it's only like a few lines of code away from like you just need to define some appropriate prior distributions and call fit and see if it's reasonably fast or not. In this very simple case here, which I guess is not that simple, it's a reasonably like it's a reasonable model. Many models are going to be of this sort of nature. Doing 200 samples on a four threads, not using like any 8 or 16 or 32 threads, is taking maybe almost 15 minutes or so, and so that's still acceptable to me, I would say, because but even though it's just 200 samples, but I can also use a bigger machine, and I'm doing a Teams call at the same time. And so overall, I would say this kind of model is not too bad. This kind of population size, we're talking, I think 31 subjects. So phase 1, phase 2, again, probably okay to use Bayesian. Phase 3 data with a large complicated model, then I would be more reluctant to use Bayesian. And if I use it, I would use it only at the end to replace a bootstrap. But during model development, for example, I might just use FOCE. So replace this algorithm here with FOCE. And then once I have a good set of parameter values, I might use that to initialize the Bayesian fit, just to give it a little bit of a push. But yeah, with like hundreds of subjects, I'm probably not going to reach out for Bayesian first.
Okay, thanks for sharing.
Thanks. Good. So we're almost there, but not quite. So any more questions? Okay. So maybe it's worth noting that after the adaptation was finished, the step sizes of the chains were all very similar. This is usually a good sign. But also the acceptance rates of the chains are also similar or close to 0.8, which is the recommended or how the target acceptance rate that we set by default. You can change it as well. It's one of the options here. And so it seems like the parameters are okay. Yeah. And the log densities of the chains are also quite comparable, and they're all reasonably high compared to how they started. So that's also a good sign.
Hi, Mohammed. Sorry,
Hi.
I have a naive question. Maybe you already explained that, but maybe I missed that. So at 587, all the parameters, they are at log normal, but except the Emacs. Why is that?
The reason is that this was the way the model was defined, and I think this is how Nick Holford prefers to define these models, is my understanding. is he makes 1 plus, and then the Emax is essentially goes from, I believe, 0 to minus 1 or to minus Emax. And so the way he defined this model, he wants Emax to be negative, essentially, in this case. And I think that's because the function is expected to be maybe going down or something like that. But again, I did take this directly from his slides, essentially. And so because this parameter has to be negative, it cannot be log normal. Technically, you can do a sort of truncated normal here, and I can set the upper bound to 0, right? So that we could also do. But log normal is unfortunately only for positive parameters. The alternative is to, I think, make this like minus here and make it log normal. So depending on how you write your model, you want to make sure that the expected domain here should be matching the domain of the distribution. The other thing is, just in case, in general, it's not a good idea to tell the model or tell the, I mean, you can look at the data and decide whether the positive Emax makes sense or negative Emax. But in general, it's a good idea to let the model decide if Emax should be positive or negative, not to bias your directionality, essentially, of if the drug is working or not. And so is the drug has an increasing effect, or let's say a decreasing effect on the PD rate of change. And so it might be a good idea, just from a pharmacometrics point of view, to leave this unconstrained, even if we expect it at the end to be negative. But the model is not going to break down if this is unconstrained. And so we just initialize it from, or we give it we expect it to be around -1. And so we give it a normal distribution prior, centered around -1 with a standard deviation of 1. So it can still be more than 0 if it has to, or if the data says so. We can make this even more widely dispersed to give it a bit more probability in the prior that it might be more than 0. But again, if the data says that this is negative, then we expect the final values to be also negative or close to -1. And I think in this particular case, that's what you see. But yeah. Does that answer your question?
Yeah, thank you. Thank you very much.
I'm just thinking out loud here, but I mean, could you also just use in the end like some MCMC sampler to replace Bootstrap and/or sampling in Pons resampling? Because I would say SEER or sampling Pons resample is kind of kind of close to Bayesian, but you don't really, but you do this repeated times, right? You always replace the prior with the kind of posterior from the first iteration, then you have multiple iterations. But surely an MCMC sampler is more efficient and more, like better at getting to the target distribution. So I'm just wondering if you could do that, but then it would involve probably multiple iterations also by replacing prior and posterior again and again until you converge to one distribution. I'm just wondering if that would be possible technically.
It is, yes, but for that you would need to be quite non-informative about the prior and make sure that it doesn't impact your final estimates too much. And so you're just using the Bayesian like MCMC to get the uncertainty estimates of the population parameters, but you don't want to impose any sort of bias at the beginning. And so that is, yes, possible as well. For some reason, it's not very commonly done. Maybe it's because people are intimidated by having to define priors. I find that that is the most difficult challenge with defining these models. And then once if you do your fit and it takes too long, or if it doesn't converge, or even if it does converge, often the people don't know what to do with that, I think. And so it could be that lack of software made it a bit more difficult to use Bayesian instead of Bootstrap. And Bootstrap was just out of the box supported in some tools, and some people use it. But yeah, I would say that that's definitely a good way to do it.
Okay, yeah, thank you.
No worries. Okay, so we have 22 minutes here. So you can definitely feel that it's not that fast compared to even like a regular FOC fit here. It took about 3 minutes, I believe. But again, that was just for one fit, and the Bootstrap took a little bit longer. But also, to be fair, you're going to need to do 10 times this number of samples usually in practice. And so it might end up taking maybe close to 9 to 10 hours for a full fit here. But of course, you can also have more threads, in which case you can cut that down maybe to 5 hours or less. So it's definitely not for the faint of heart, but it does need a little bit of patience. And perhaps at the beginning, you can start with a few samples, see if your model is doing okay. Maybe initialize it from the FOC EFIT here just to give it a little bit of a push. That's some pure Bayesians would not like that idea in general, to try to initialize the fit like this using the data. But from a practical point of view, that can end up saving you maybe a good hour or so of sampling. So I don't see the problem. And technically, if all the chains converge at the end, then the distributions should match regardless of the initialization. And so it's not too much of a problem in an asymptotic argument. Yeah. But again, beyond that, it's the challenge is really finding appropriate prior distributions for your parameters. But once you get past this hurdle, I think from a software tool point of view, it's quite straightforward. What you can do here, just replace a domain with a prior and then call fit with a different function. And now that we have the output of fit, so let's first take a look at the outputs here. So Bayes, FBM, if I just display the output. So we have this automatic or default output that we display. It's compiling once again, so I'll just give it a few moments. So here it will display some summary statistics and diagnostics for the different population parameters. And so things like the mean, the standard deviation of the distribution, the Monte Carlo standard error, which gives you some idea about how convergent your chains are. And that's a function of the effective sample size. It will give you some estimate of the expected effective sample size, the bulk one and the tail one. Again, for more details about this, you can visit some of the Bayesian literature. And then we have this R-hat diagnostic, which we expect to be close to 1. And you see that because we have very few samples, and actually this is really a bad sign that the chains have not yet fully converged. But the hope is that once we have more samples here, we can get an R-hat that's closer and closer to 1. And then this is the effective sample size per second. Again, that depends on like towards the end, you expect that the effective sample size per second will pick up as your sampler becomes more efficient at getting sort of near independent samples, whereas at the beginning the samples might be highly correlated. In part because you're moving towards, let's say, the high probability density areas, and just by definition, if you're moving towards one area, all your samples are going to be correlated, and so the effective sample size discounts the number of samples that you have based on the correlation, the average correlation in your samples. And so even though we sampled 200 samples here, or 200 times 4 actually, so 800 samples, the effective sample size was only about 8 for this particular parameter and 19 for this parameter because of the heavy correlations or autocorrelations between the consecutive samples. But again, for more details, you can consult the paper and some Bayesian literature. But the idea is that you get all of these sort of standard diagnostics out of the box. Now, if you want to look at the parameter values, and in particular, let's look at the Emax, you will see that the quantiles, so this is a 2.5 percentile of the posterior samples, the 25th percentile, 50th percentile, 75th, and 97.5th. You'll see that all of them are reasonably centered around 1. And that's a good indication that basically maybe 1 was a good idea. And you'll see that the standard deviation of this Emax parameter here is actually 0.073, even though in our prior distribution we allowed it to go pretty like we gave it a standard deviation of 1. Right, and even though it was centered around -1 as well, but it's fair to say that the data also supports this hypothesis essentially, or this claim, because it could have easily gone away from -1 because we gave it a lot of room to go away from -1 by giving it a standard deviation of 1, but it actually chose to be more centered, or to be centered around -1, and then have a very small standard deviation as well in the posterior. So you can sort of try to interpret the values that you have here and what they mean. So if this is like if you have one of those parameters is a drug effect, for example, then you can take a look at the sign of the drug effect. seeing if this interval here, which is sometimes called the credible interval, so it's the interval going from the 2.5th percentile to the 97.5th percentile, if this credible interval includes 0 or not, for example, for a drug effect parameter, and that will give you an idea about whether that drug seems to be working or not, and with what probability can you say that. So this is technically just the naive way to calculate the credible interval. The actual credible interval is usually calculated as the smallest interval that has 95% of the samples, but you can also just use this naive estimate using the percentiles directly. But there is another way to estimate the credible interval, which is the smallest interval that contains 95% of the samples. Okay, so again, you do have this information, and you see that it's no longer a point estimate. It's not just one value of each parameter. You have a whole range of values here. And so we have all these different samples that now we can use and simulate from and do all sorts of things. So let's take a look at what we can do with them. And so first, what we can do is call this discard function to discard the burn-in samples. So maybe we don't want to look at all of the samples, but just the ones that have been cleaned up from the initial sort of like adaptation phase. And so this here will throw away about 50% of the samples. You only have about 100 or exactly 100 samples per chain and 4 chains here. And you will see that the effective sample size decreased a little bit for some parameters because we always, whenever you decrease the number of samples, you always decrease the effective sample size as well. So they're correlated. So yeah, but in any case, this is going to be, again, the same sort of outputs, but just for the truncated, essentially, chains that we have here. Now, let's say I want to get the mean values of the parameters from their posteriors as the name tuple. I can call the mean function directly on this, and this will give me a name tuple that has all of the mean values of the parameters, which can help me maybe easily, like I can send this to somebody and interpret this somehow. I don't know if STD also works. I think it does. Good. So you can also get the standard deviations of these parameters as well as a name tuple. Okay, and we can why is that here? Okay, this was here by accident, I believe. Actually, no, this was probably here to compare the means to the coefficients that we got earlier from the non-Bayesian fit, right? And so if we look at these and try to compare them side by side, so you will see that the values are actually pretty close to each other, right? The mean of the posterior are close. Actually, not in every case. So this one, for example, is different, right? But it's hard to know whether this is because the Bayesian didn't converge yet or because of some other reason. But this pub_tabs, for example, did not converge yet or is not matching 94 versus 96, but overall they seem to be sufficiently close. Right, so it's maybe that gives you some confidence in these parameters. Yeah, we'll leave it at that because again we can't really rely much on the on just 200 samples here, and so it'll be difficult to make any kind of conclusions. And if you want to double check whether or not your parameter converged, and so I can use this density plot function to get some diagnostic plot, which is going to be the density plot of all of the chains for a particular parameter or a set of parameters that I can decide. And so I can get the density plot of this pop_t over, which is the population parameter for turnover, I believe. And it should give me some density plots out of that. And as you can see, the chains did not converge. They are 4 different distributions. And what we expect is that when they converge, that they should all overlap. So this is like a continuous histogram, essentially, or a density plot for the samples that we have. And we expect these to be matching one another at the end of a good fit. So this is not converged yet, as we can see here. Good. There are many other diagnostic plots that you can take a look at. We already looked at the metric, the R-hat metric, and then we looked at the density plots, but there's a lot more that you can take a look at the paper and the documentation and tutorials for to get more information about that. Now, another thing we can do here is, so what was the Sims to So if you remember, we had this SIMS2 defined earlier, and it was just simulating from the model that was not a Bayesian model, and it was simulating 100 scenarios for that model. And then we can call the reduce function with vcat in the first argument to flatten this. Instead of getting a vector of vectors, we can just get a single vector with 100 times the number of subjects, which is 31, and that can give us this here. And so in this particular part of the code, I am demonstrating how you can use this post-process function. But before the post-process function, I want to show you something else. So technically, you can also simulate from, or not technically, you can simulate from the. So let's define a new Sims3 here and simulate from the output of this Bayesian fit or this truncated here. So if you call this SimObs here, it would basically do a posterior predictive simulation where for each sample here, it will attempt to simulate a response. And so for each subject as well. And so let's see what we get out of it. And here it's telling you that it's actually sampling all of the samples. So this is a mistake here from the posterior predictive distribution. So it's sampling some number of samples from the posterior predictive distributions of each subject, and this number of samples by default will be the same as the number of samples here, which is 100. You can actually explicitly pass, for example, 100, and it would tell you here that it's sampling 100 samples. So we'll just give it a few moments while it's simulating. Okay, so it provided a large number of samples. It's actually 400 because we had 100 per chain and 4 chains. And so it provided 400 samples for each subject. And so we had 31 subjects and we have 400 per subject. And so total is 12,400. And it provided this as, if you look at the type of this, it's a single, I believe, flat vector. Yeah, it's a single vector of simulated observations that has all of these simulations inside of it. In the previous case, we had this, we defined our own sort of vector of vectors of simulations, and so we had to reduce it ourselves with the reduce vcat function. And so you can also do that whenever you're defining your own simulations here. You can reduce it yourself. But once you have this flat vector of simulations, you should be able to call something called the post-process function. And so let me remove this plot here and just give myself a little bit more space. So this post-process function works on any output of simulation. So I can use it on Sims3, which I just simulated from the posterior. And the way it works is it allows you to query the or define some derived quantities directly based on the simulations that you have, and also based on the observation. So maybe you want to get things like what people call the Bayesian p-value, which is the probability that the simulated value is higher than the observed value. So you can easily do that, for example, by just getting so gen here. So let me explain the syntax first. So this is a syntax that we haven't discussed or seen before, but this syntax in Julia, if I have something like this where I'm defining an anonymous function that takes an input x and outputs x squared, and then let's say I'm mapping it over some random vector or vector of length 10. This here, another way to write this is using this do block syntax. And so I can write it like this, essentially, where the only difference is instead of writing the anonymous function here, I am writing the anonymous function here, right? And so it's just a different way to write an anonymous function and then pass it as the first argument of this function. And so this could be any function. This could be like reduce, right? Or in which case, I mean, maybe not reduce, but it could be like map reduce, for example, which also expects a mapping function at the beginning. But it could literally be anything that expects a function at the beginning. And I can, instead of writing the anonymous function like this, I can write it in this syntax here. And it could also be, actually could also be reduced, but this now would need to be x1 and x2, and then it would be x1 plus x2, for example. So this is like the sum function here. but then I would need to get rid of this. So this is like me writing this sum function. But the idea is that this here is just a fancy syntax for defining an anonymous function that takes this two inputs, gen and obs in this case. Gen stands for the generated quantities, and obs stands for the observed values or the observed quantities. And so we have the generated, for example, concentration, but we also have the observed concentration. In there, we have the generated PCA, but we also have the observed PCA values. And so what this allows us to do, this post-process function, which again, I could have written it in a different way. I could have written this as an anonymous function here. So this could have been done like this. This is an anonymous function, and then it returns this. And then I could have defined this function like this and then passed it as the first argument here, right? So this would have been identical, essentially, just defining an anonymous function and then passing it here. But this syntax is a little bit cleaner. So we're going to use this do syntax because it's a bit cleaner. So this do syntax, the way to think about this, the post-process function is very similar to the map function, essentially. So what we're doing is we're mapping over all the simulations. And inside the function, now we have access to gen, which is all the generated quantities from the model. And so this includes all the outputs of the pre-block, for example, the derived block dynamics, etc. So you can literally use any intermediate quantity from the model here that we defined. So CP or rate n, maybe not these because these are not stored because we use the colon here to not store them. But you can use things like like you have access to the simulated concentration, simulated PCA, the depot, central, turnover, etc. Right, and if you even have an observed block here, so we didn't cover observed block. But this block allows you to define further things that you want to save. So maybe I want to save CP, for example, or save maybe a turnover. So to save or say, let's call it CP turnover, and let's say I want to, for some reason, save the sum of those, right? And so this would you also have access to that at the end in the simulation. And so all these intermediate quantities that you defined throughout, including all of these values, you should have access to them. And the idea is that you can now use this post-process function to extract any kind of function of these values or the values themselves. So I can just extract directly, for example, the clearance. And now clearance here would be a function of time. And so I can extract the first clearance, for example. And so or not a function of time rather, but it's a vector with one element per time point. And so in general, all the quantities here, or most of these quantities here that are time-based, will be a vector one per time point in the simulation or in the data. But yeah, so you can use this post-process function to extract things from your simulations, essentially, or to compare your simulation and your observation in some complicated way. Instead of going to a data frame first, which you could also do, go to a data frame first and then do this over there. You can also do it directly based on the simulation output. So in this case, I'm actually calling the nca.auc function, which just calculates the area under the curve for the concentration points using the trapezoid rule. And given some time points that the concentrations are observed at. I'm also getting the Cmax for the generated or the simulated concentration and using also the generated time. I'm actually not using this at all, so I can also just replace it with underscore here. It's not being used. Or I can leave it. It's just not being used. And at the end, I'm actually returning a name tuple. So this is a name tuple. I remember mentioning yesterday that if I write a name tuple, I can write it either like this, or if this here is also called PKAUC. So if the name of the field or the name of the value and the variable holding the value have the same name, then technically I can remove one of those, and Julia will automatically expand it like this. Right, so all of this just means literally I'm writing a name tuple. The key name here has the same name as the variable name, and so that's why I'm omitting these. You can omit only some of them and leave the others. But this post-process function will essentially return a name tuple for each simulation. And this name tuple will be the AUC, the PKAUC, the PKCmax, the PDAUC, and the PDCmax. Right, and so let's take a look at that. And you'll see that there's a lot of So some of these NCA AUC functions and Cmax functions are actually failing because the simulations are not very good. I think the simulations may be negative for some of these, and so maybe that's why it's giving me some errors. And so some of these are not going to give you a number. They might give you nans, but then you need to take that into account when doing some summary statistics at the end to discard those simulations, or otherwise go back and try to figure out why your simulations are not good. But we already know why, because the Bayesian fit did not actually convert. So, and maybe that's why I actually used this reduced SIMS2 because it was probably a better set of simulations in general. But let's use SIMS3 for now. But again, you can do this with any kind of simulation. So I mentioned yesterday that we're going to revisit simulations today. And so you can do this with any kind of output of SimOps because they all have the same type at the end. You just need a vector of simulations here. And then you can call the post-process function. And so now NCA params will be having the same length as the simulations, but now it will be a vector of name tuples, essentially. And so I can take a look at the first one here. And the first one is this name tuple, where for some reason the PKAUC could not be calculated, gave a numerical error. But the second simulation, it was fine, right? And then the third simulation, but actually the PDAUC could not be calculated in the second simulation. But yeah, but the point is that you have all of these simulations here that you can post-process in different ways to define all these additional quantities at the end that you would like, that are derived from the posterior predictive simulations here or any other simulations for that matter. Good. Then once I have this vector of name tuples, I can call the same do syntax or use the same do syntax, but with the mean function. So the mean function also accepts, so I can, for example, give it the absolute function here, and then I would like to get the mean of this vector of 3 numbers, but first transform it by the absolute. It's the mean absolute value that I'm interested in. So the mean function has a method. So beside calling the mean function like this, I can also call it with a method or a function as the first argument, and this function should only take one input, and then it just every input here or every value here is first passed through this function before we get the mean. So it's going to be the mean absolute values in this case. And so because I can write it like this, I can also write it like this. And for example, just absolute of x, right? And so here I can, this is the same thing as this anonymous function, right? And so in this case, we don't need to write an anonymous function because I can just pass the function directly as an object. I don't need to create another function that just calls this absolute function, but it's equivalent, right? This is equivalent to this. And then these are all equivalent forms to write the same thing, right? And so this is a perhaps more readable form when my function is doing something more complicated or it's multi-body function. So maybe I want to define first some temporary value and then do like this, like maybe I want to do something more complicated here, then these two forms become less readable. Well, this one becomes not possible because I need to define my own function, and then this one becomes less readable. So we use this. So in this case, I'm using this particular form of calling the mean function with an anonymous function passed as the first argument. So the anonymous function takes a single input p, and what it does is it checks that the AUC, so p is going to be the name tuple. So p is going to be each one of those elements here, which is the vector of name tuples that we just got, right? So the name tuples will have these fields, the PKAUC field, the PKCmax field, PDAUC, and PDCmax. And so here what I'm checking is I'm checking that the PKAUC field of that name tuple is not missing first. And that it's within some criteria, some therapeutic range that you can define based on this particular drug, or based on some other simulation, for example, to determine what's a good efficacious interval to aim for this AUC. And then I also want the Pmax, or sorry, the PKCmax to be less than a certain number. Now those numbers were kind of made up numbers, and so they're not necessarily accurate, but you can see that you can define whatever criteria you want here. And this at the end will actually return either true or false, right? And so it's a Boolean, but then because I'm taking the mean value, so when you take the mean value of a bunch of Booleans, So let's say true and true and false. It gives you an estimate of the probability of, or essentially the ratio of truths in there. And the ratio of truths, if from a probabilistic interpretation, is essentially the estimate or the maximum likelihood estimate of the probability of getting the true outcome at the end, right? And so I can get the mean value of a Boolean vector essentially to give me an estimate of the probability that this condition here will be satisfied given the posterior samples that I have. So given all of the posterior simulations that I have. And across all subjects. Now I could be doing this simulation per subject. So I can only maybe simulate for one subject here, and I can show you how in a second, instead of all of the subjects. And in that case, this simulation can be pertaining to just a single subject, and it's considering the posterior of that subject. But usually with dosing decisions, for example, if you want to use this to select a dose, which is what we're going to do next, you want to do it across the whole population because the dose is going to be given to everybody. So you want to make sure that you can satisfy whatever therapeutic range that you have and the toxicity upper limit that you have for all subjects sort of as a whole, as you want to maximize this probability essentially as much as possible for, again, some therapeutic criteria. So let's do this here and let's see what's the probability that we have. And we'll see that the probability of satisfying this criteria right now is 71%, which is not too bad, but not great, because about 30% or 29% of the scenarios, which could mean 29% of the subjects, essentially, you could interpret it that way, might be violating this criteria. In the future, like future subjects that have not been observed yet. And so because of the probability here we use all the subjects together, you could technically interpret it this way, that maybe 29% of all future subjects that might occur or might happen or might come in real life might not satisfy this criteria. Assuming, of course, you converge to the true posterior and that you have enough samples to make such an assertion about future subjects and so on. So there's a lot of assumptions behind this statement of mine that I just made. But yeah, another thing we can do here is just to look at the histogram of the different values. So I can look at the histogram of the PKAUC, and the way we do this is by calling this get property function. Now, get property is nothing but, so if I do it like this, and then PKAUC. So this here is a vector of name tuple, right? And this here is going to be the name tuple. And so get property is equivalent to writing it like this. So accessing a field with this dot notation is the same thing as calling the get property function with the field name as the second argument. These two are identical. In fact, this one will under the hood expand to this one. And so this here, I'm just calling the get property function with the broadcasting because I want to get the field, the first field here, or this PKAUC field from each element in that vector. So I'm broadcasting the get property function to call it on each element of the vector, and I want this to be the second argument for all of the get property calls. And so it will be getting the PKAUC for PKAUC values for all of the simulations. So it returns a vector of float 64s and missings, because sometimes it's missing and sometimes it's a float 64, and so it returns a vector with the same length, but with the actual PKAUC values inside of those named tuples. And so I'm using the function form because then I can broadcast it. I cannot broadcast this dot because it doesn't work in Julia, but I can broadcast the function get property like this. And then we have, this is the pipe notation that I said. So I discussed also, I think on day one, where we can take the output of one operation or one function and then pass it to another operation or another function. And so here I'm taking this vector of missings and float 64s, and I'm calling the skip missing function, which will ignore or create an iterator that ignores all the missing values. And then I'm calling the collect function to get a vector of all the non-missing values. So this only creates a lazy iterator, and then collect will actually collect the non-missing values. And then I'm calling the hist function, which calls or draws a histogram. This is just a one-liner that makes it easy to define a histogram for all the values. And you'll see the histogram is not a very good one. It's all very concentrated here. And I'm pretty sure I can play with the options of the histogram to give it a bit more bins. I think there's maybe only 2 bins here. There's a very small bin here. But let's take a look at some other histograms. So this is the histogram of Cmax. You'll see that Cmax is a lot more distributed here. And then the histogram of PDAUC Again, a good distribution here. There's probably a bunch of bins here that are all too small to see. Maybe that's why it created a plot like this. But all of them are actually concentrated here. But if you look at the other distributions, they all look sufficiently dispersed, right? And now the next question is, how do we actually use this code that we wrote or some version of it to do dose optimization? So I've shown you how you can simulate from the posterior distributions and like using the same samples that you got, but also using the same subjects. So we're not changing the subjects, meaning if we look at the covariates here, we're going to, for each subject, we're going to use the same covariate values. We're going to use the same dosing regimen that was passed to the subject. And so we're not really changing what the subjects are. We're just changing the response. Right now, if you want to change some of these quantities and do all sorts of what if analysis, for example, you want to find out what if I increase the dose, and so that's one of the things about the subjects that I want to change, then that's called a counterfactual simulation, because it's something that did not happen. But for this particular subject, if I keep everything else the same, if I keep all the covariates the same, but I only change a dose for that subject, then what's going to be the effect of that? Like I want to study the effect on the output at the end. And the reason that this is useful is that I can use it now to try a whole bunch of different doses and then compare the outputs or calculate some probability of achieving therapeutic success based on the simulation outputs, and then pick the dose that gives me the best results or the highest probability. So I can, once I define a function that can do this, given a new dose, it can simulate from this new dose for the subjects, and then it calculates the probability of therapeutic success. Then I can try to optimize over this dose amount and pick the best dose that maximizes the output of this function. And so that's exactly what we're going to do next. So let's take a look at this here. And it's here I'm using a whole bunch of different topics or like functions that we've discussed so far, and hopefully you can see how they all come together. And so the first thing I'm doing is I'm getting all of the IDs from the data frame directly. So DF2 here, if we go to DF2, it was the data frame that we defined earlier at the very beginning of day one, or the very beginning of this case study, where we defined the data frame that we then read into Pumas as a population. So this is just the data frame representation of our population. Okay, and so if we go down there again, so here I'm taking the ID column from that data frame in this case with this .id notation. And so this is giving me a vector now of IDs. So let's take a look at it outside. And so this is giving me a vector of IDs, one for each row. And then I'm calling the unique function on that. So the unique function will just remove any duplicates. And so it should give me a vector of 31 IDs, right? Now there are 31 IDs, but we removed one of the IDs, I believe, or one of the I think the numbers are not consecutive, if I remember correctly. So we have up to 32, but one of these indices is skipped. One of these numbers is skipped. But we do have a vector here of 31 IDs, essentially. And so I'm getting all the unique IDs here, which, by the way, I can do outside the function because this doesn't change. So there's no need to call this over and over again. So let's use it outside the function. And then here, what I'm doing is I'm taking like one of the inputs. Let's discuss the inputs first of this function. So this function here is a function that I'm defining. It's called new dose sim, stands for simulation. It takes in as an input the output of the Bayesian fit. So this here is the output of a Bayesian fit. So let's just write a multi-line comment here. So this is output of the let's say Pumas of discard function, which is after removing all the adaptation steps. Here, this is going to be the subject index that I'm interested in simulating. Here is going to be the number of simulations that I'm interested in having or making. And this dose multiplier is going to be like the new dose equals old dose times the dose multiplier. So I'm going to multiply the old dose of the subject by this number here. So if this number is 1, then the dose doesn't change. And if this number is 0.5, then I'm halving the dose for the subject. And if this number is 2, then I'm doubling the dose for the subject. Right, because every subject had a different dose. And so I'm defining this dose multiplier that decides, again, whether or not we should halve or double the dose, for example, right, or multiply it by any other ratio. And then ops times is just the simulation observation times. Right, so this is all the time points over which we're going to be simulating. And here I'm defining all the simulations from time 0 to time 150 and over a step size of 1. So we're going to be using this to then calculate, use to calculate AUC, for example, in Cmax, right? All the simulations here. Good. So let's start by looking at this code. So this code here is going to be, let's say I define I equals 1, right, initially. It's always a good idea to take code out of a function, see what it does before you then put it inside a function. And so if I call this at R subset macro, and notice it doesn't have a bang, so it's not actually modifying the data frame, it's just subsetting the data frame for us. And based on this condition here, and this condition says that I want only the ID that matches this ID's I. So ID's I is going to be, I forgot to define I. If I is 1, and I forgot to define IDs. So if I is 1, then ID's I will be this string 1, or 1 as a string. And so I would like to only take the part of the data frame that has this ID equals 1. And so this is basically the subject data frame, right? So this is an individual data frame here for one subject. And so let's take a look at it. And so all the IDs here are equal to 1, and it's just we have different rows or different time points. Now, next, what I'm doing here is, again, this is a different data frame that doesn't modify this data frame. It's a copy of only some of the rows of this data frame. And so I can easily modify this now without worrying about modifying the original data frame. And so what I'm doing here is I know, because by looking at the data frame, I know that the amount is always on the first row of this data frame. If I don't know this, then I can just multiply the whole column essentially by a certain dose multiplier. In fact, let's do that. We can just multiply the whole column here by a certain multiplier. So here I'm taking this dose multiplier that was input to me, and I'm just multiplying all the amount field. And when it's missing time is a float will always give you missing, so it doesn't change anything. And so let's actually do this outside here as well. Let's define some dummy dose multiplier. Multiplier. There you go. And let's then try to modify the subject data frame. As you'll see that if I now take a look at the subject data frame again, you'll see that the first dose now became 200 instead of 100, or the only dose really in this case. But this here is just a way to essentially double the dose in this data frame, right? And so let's get rid of these. Now, the next thing I'm doing is I'm calling the read Pumas function on this same data frame. So I'm literally using the same read Pumas that we used earlier. So if you go up here, this is the same read Pumas, but instead of the entire data frame, I'm reading it just for a single subject, right? And this is where you can see that having access to a programming language allows you to do all these flexible things that I can not just like I can do a fit or a simulation with a subset of the data quite easily, even inside of a function. I can define a function that allows me to do this systematically and change some part of the data frame in a programmatic way. Right, so it's really quite empowering, especially if you want to do some complicated simulations or decision making that involves a lot of clinical trial simulations. Then being able to define your own function actually can help a lot. And so in this case, I'm just reading this subject data frame into Pumas as a population. Now it's going to be, I'm using the exact same function call. The only difference is now I'm actually, I know this is going to be a vector of length 1. So I'm getting that subject out. So let's call this read Pumas function outside again. Okay, so if you call this read Pumas function outside, it's going to give you a population or a vector of just one subject. And so when I get the first element of that, it's just going to give me an individual subject here or a subject struct. And so that's what I'm doing here. So I'm just defining a new subject and Pumas subject using the read Pumas function straight from the data frame. Now, what we could have done is actually, instead of doing all of this, we could have directly accessed the subject from the population. So we could have just tried to access the subject from the population like this, and then try to modify the dose. So there is actually a way to also change some values of the subject in Pumas itself. So there are other ways to do this, but I thought that this is the most general way, because being able to, like in the data frame, you can modify whatever you want, right? And so it allows you to do all sorts of changes. Whereas in the function that we provide, it maybe allows you only to change the covariates or the dose or something like that. But this here, you can change whatever you want. And so I thought this might be better to showcase, although it is a bit more verbose, but also it helps us demonstrate all the same features that we saw at the beginning. So maybe it's a good educational exercise. But again, to recap, what we did here was we took a subset of the data frame for the first ID, or whatever ID we decide, whatever subject we decide here, 1 to 32. This can go from 1 to 32. And then we subsetted the data frame. We multiplied the amounts column by the dose multiplier, and then we read this subject data frame into read Pumas, and this is only going to be a single subject, so we took the only subject here out, and now we're calling the simobs function. So now we're doing a simulation inside this function, and this is a new way to call simobs that we haven't discussed before, and that's the counterfactual Bayesian simobs. And so the sort of with regular simobs, you can always like pass in the empirical Bayes estimates, for example. So if this was not Bayesian, you could have easily defined a new subject and then passed the empirical Bayes estimates as the fourth argument of simobs. But with the Bayesian simobs, we actually have a special method, because we don't just have a single value for the empirical Bayes estimates or the mode of that posterior of the random effects, but we would like to use all of the posterior samples for the random effects for a specific subject. And so when I said counterfactual simulation, and I said that we can change the covariates here, I meant that we can also, or we should retain the posterior distribution of the random effects. So we don't want to use the prior. We're not assuming that this is a new subject. We know that this is the same subject that we observed the data for, and so we have some good values for these random effects for this subject, and we would like to reuse those values, the posterior samples from the random effects of this subject, but only change one of the covariates or change the dose. And so in order to do this, we have a special function that allows you to essentially reuse the posterior samples for subject 1 or subject 2 or subject 3, but also change the dose to see what happens if I change the dose for this subject, but then that will not have an effect, or it should not have an effect directly on the random effects of the subject. And so those we can still reuse from the fit, essentially. Now, if you want to simulate for a completely new subject where you're not using the posterior samples for the random effects, but you can still use the posterior samples for the population parameters, but then also sample from the prior here, you can also do that. So this would be simulating for a completely new subject that was not observed yet. What happens if we only sample from the posterior samples here, but then we sample from the prior of the random effects. So you can do both kinds of simulations. And so here I'm showcasing the first type, which is the type where we're retaining the random effects posterior. So let me go back here. Over here, I'm passing the same output of Pumas.discard. I'm passing the new subject that I just defined. So this here is the new subject, right, that I just read from read Pumas. So this is the subject that has the new dose or the new covariates or anything new that I'm trying to test as a counterfactual. And then I'm giving it the subject index I, which tells Pumas or tells simobs that I would like to use the posterior samples from the ith subject. So if you drop this, actually, it should just sample from the prior. But if you give it this subject, then it will sample from the posterior of this subject I. And so you can tell it that this is actually the same subject as subject I, except for I want to test what happens if I change one thing about it. And I'm passing the new subject here with the new dose, but I'm also passing it the subject index, so it knows which posterior samples to use for that subject. And then I'm also telling it how many samples to use or to simulate, essentially, from the posteriors. And then I'm telling it how many or which observation times to use. And so I believe I did not define observation times. So let me copy this here. And if I had a variable already called observation times, I didn't need to write it like this, equal. I can just write it like this, but I can also write the values here. So let me go ahead and call simobs, and I don't have nsim defined. So let's use nsim equals 100, or the samples equals 100. So again, let's recap what this is doing. This is doing a counterfactual simulation for subject I. or the first subject of the population, essentially, and it's using a different dose or different covariate or different background for the subject, which is a counterfactual simulation, and then it's trying to see what happens if we change the dose for this particular subject. Okay, and so that's a simulation. That's a counterfactual simulation in Pumas Bayesian. Now, as I said here, if you drop the samples, the subject equal, so actually here it tells you exactly what's happening. It's simulating 100 samples in the first case. So in the case where we had subject equals I, it simulated 100 samples from the posterior predictive distribution of subject 1 using the dose and covariates in the input subject, which is this subject here. All right. Now, in the second case where I remove the subject equals I, it's telling you that it simulated 100 samples from the subject's mixed posterior prior predictive distribution, where the posterior distribution is used for the population parameters, but the prior distribution is used for the subject-specific parameters, right? And so this is just giving you a bit more details about what's happening here, so that you can take a look at it, or you can hopefully not mix things up. So that's what this line of code here is doing. Okay, so we went through this line of code. This line of code is literally the same line that we had earlier, where we just used the post-process function, which takes this, again, anonymous function as first argument, which we're using this do syntax to define, and it's using or defining a name tuple of the AUCs and Cmaxes. So that's the same previous line that we discussed. And then here, this is also the same line that we discussed previously, where we're just trying to calculate the probability of fitting in some interval here. And I changed the intervals a bit, but again, those are made up, so you can easily change them yourself. And this is going to give you the probability of, or an estimate of the probability of matching this specific criteria here. And at the end of a function, I'm outputting three things. I'm returning three things. They return in a tuple by default. The parentheses are optional. But here I'm outputting the simulations, if in case I want to take a look at it. And I'm outputting the output of post-process. And I'm also outputting the probability value at the end. And this is what I'm interested in maximizing, essentially. And so if you look at this function, there will be a decision. The decision is maybe the dose multiplier, and there will be the objective that I want to maximize, which is this probability. So you can kind of see where this is going. And so let's go ahead and define this function here first, and then test it out. So here I'm passing to this function these four inputs. So the output of Pumas.discard, the subject I, or I, which is the first subject, the number of simulations per subject, or for this subject, and 0.6 was, I believe, the dose multiplier. So if I remove 40% of the dose, what happens? And then I'm not passing it the ops times. It's just using the default value for the observation times here. So I don't need to pass the last one. So let's go ahead and call this here. And here I'm unpacking. So if you look at this, I'm unpacking the outputs of this function to these three variables. So this is the simulation, and this is the NCA parameters for the simulation, and this is the probability. So I'm unpacking these into, again, three different variables here, essentially. So this is how you do a multivariable assignment in Julia. And then I'm just taking a look at the probability, and now the probability is 0, which is not good. And so let's see if we can change it. And so yeah. But before we do that, so I'm going to show you now how we can optimize it. And I think the original code was actually running on the output of a bootstrap simulation rather than the output of the Bayesian simulation. So changing that might change the results a bit, but we'll see how that goes. But the point is that we're going to do the optimization in a second. But before that, here I'm just demonstrating again how you can simulate for a new subject. So a new subject means you want to simulate from the posterior of the population parameters. So you want to use the posterior of the population parameters, but you want to simulate from the prior for the random effects, because we don't have any data for this new subject yet. And the way you do this is, again, using the same simobs. You just drop. So you still need to pass the subject as a second argument, but you drop the subject equal I keyword argument. This one can be dropped, and this will have a different simulation behavior. Any questions at this point before I go into the optimization? Okay. So as you can see, when we call this simops here, we see a lot of this information printed. right? And if we can, some functions, for example, may have a verbose keyword argument that allows you to turn off these info statements just because I don't want to see this 100,000 times if I'm running this 100,000 times. And so in case you don't have this option of verbose equals true or false, I believe SimOps does not have this option. What you can do is use Julia to actually hack around bits and make sure that you redirect all of these printed statements to a file. So this is, I'm demonstrating how to do this now. This is just Julia. This is not Pumas, but here I'm like this kind of construct. So let's ignore everything here for now. This kind of construct, what it does is it opens a new file called warnings.log. You can give it any name you want and any extension you want. And then I want to write to this file. And this is using the same do syntax here. So it's convenient because I don't want to define everything as anonymous functions. And I have a multi-line function here that I want to use. And so this open function takes an anonymous function with a single argument or a single input. And so this argument is IO in this case. And what I want to do with this IO, and this IO represents essentially the input-output stream of this file. So I can use it just like it basically represents the file in some ways. And then what I want to do here is redirect the standard error channel for printing. So when you print this information blocks, it goes into this sort of standard error channel of printing on your terminal. And so you don't want to, I want to redirect this from the standard error to this IO, which represents the file. So I'm basically redirecting all the warnings and all the errors or all the warnings and all the info statements, etc., to this IO, which is a file, right? And then inside I can call any Julia code that I want. And if it spits out a warning, this redirect standard error will redirect it to the file. And so I'm not going to see it on the console or on the terminal anymore. And I will see it at the end in a file once the code is finished running. So I can then inspect this log file at the end and take a look at all the warnings, for example, that I had throughout the fit or throughout the simulation or anything that you want to log. So this is just a little bit of logging functionality that Julia has that allows you to redirect logs. Good. So how are we doing the optimization? I call it optimization, but maybe I should just call it exhaustive search, because what I'm going to do is I'm literally going to try a whole bunch of different doses or dose multipliers in this case from 0.1. So that's going to 10% of the dose to 3, which goes to 3 times the dose. And then I want to do a few more simulations now. And then I want to try out all these dose multipliers. So here again, I'm calling map with the do syntax. All right. So I'm mapping over all these quantities here. And I'm passing it a function, an anonymous function, as the first argument, which takes only a single argument, dose multiplier. So this will be each one of those numbers in this vector or in this range will be a dose multiplier. And then I'm calling the function that I defined earlier, this new dose sim function here, right? I'm calling this function with all of these inputs here and the dose multiplier coming from the map. So the dose multiplier will be coming from the map. And then because this function returns 3 different outputs, I'm getting the third output here. Right, which is the probability essentially. Third output is the probability that I'm interested in maximizing. So the output of this map here will be a vector. That vector will be the same length as this vector here. And so for each dose multiplier, I'm going to get a probability essentially, right? So I'm fixing all the other inputs here. These are not changing. And all the other outputs, I'm throwing them away. I'm not interested in the first 2 outputs. I'm just interested in the last output as a function of the dose multiplier. And that's what this here is giving me. So let me go ahead and call this. As I said, this is running, when I was trying this out, I ran it on the output of a Bootstrap simulation. So it might not be the same results. It might be surprising, but we'll see how it goes. So we do not expect now to see any kind of logging here because we're redirecting it to a file. But what you should see if you're running this is that warnings.log has been created, or it might be created towards the end, I believe. I'm not sure actually, but eventually you will have to see, or you'll be able to find this warnings.log. And this one here is doing this many simulations, about 30 different dose multipliers, or it's trying 30 different dose multipliers. For each dose multiplier, it's doing 500 samples. for the simulations, and I'm doing it only for subject 1, by the way. So I'm trying to find out what's the best dose for this subject, this specific subject. So you can think of this as like personalized dosing. In some ways, where I'm interested in just a single subject, and I'm trying to find out what's the best dose for this subject that I want to give. Now, what you can also do is get the sort of do it for all of the subjects. So you can modify this code. You can probably see how to modify this code to do it for all of the subjects, where you can do this, for example, for I in 1 to length of IDs, right? And so, or maybe not here, but you can define another function actually does it. And then for each I, you can get the probability, and then you can probably get the average probability across all of the functions. So you can define, so this here, for example, you can do like mean, and then 1 to length of IDs, right? And then you can call this J, for example. Let's call it J. Let's call it I. And then here you can replace this with I, right? And so in this case, you can then get the average probability across all of the subjects, right? If you really want to do that. And so you can see where this do syntax actually shines is when you have nested closures like this, or nested functions like this, or functions that take other functions, right? So this is where it becomes a bit more readable to write it like this, rather than to write everything and squeeze everything in the first argument here. But here we're only considering a single subject. So let's stick to that. Okay, so now I'm using algebra graphics, which is the sort of ggplot equivalent in Julia, to plot things. And so I would like to plot the dose multiplier on the x-axis and or my data here. So instead of passing a data frame, I'm passing a name tuple as my data, which is valid because the name tuple is like has a table interface. Like you can think of the name tuple as like this is the first column, this is the second column, right? It's a name tuple of vectors. And so I'm passing the name tuple as my data instead of a data frame, which is valid in algebra graphics. And then I'm saying that I would like the dose multiplier to be on the x-axis, which is going to be called dose multiple, and the probability of successful treatment, or prob, is on the y-axis. And so let's see how that works for this particular subject. And it might look very odd, in which case I can, oh, it doesn't look too bad. Good. So yeah, so now if you look at this, you'll see that when we tried remember when we did the initial probability here, the probability was almost 0, right? Or actually exactly 0. And so, but looking at this, I think maybe it was a different simulation because we only did like how many simulations here? 100, not 500. But you see, it's actually if you do more simulations, you might get something more than 0. And so that's for a dose multiple of 1. But for this particular subject, maybe a dose multiple of 1.4 or 1.5 might be the best. So you can take a look at this here and judge that, or you can just take a look at the probs here and do find max probs. Find max probs, and this will find you the maximum value of this, and the maximum value is 87%, and it happens at index 20, and so index 20 is going to be a dose multiplier of 2, actually. So the maximum value happens here at this one. And so, yeah, so you can see that, anywhere from maybe 1.4 to 2, maybe you want to opt for the smaller dose to reduce, the risk of the dose. But this should give you a reasonable value for the therapeutic success, at least compared to this initial dose that we have here. Defining therapeutic success as this by this criteria here, which you can define yourself for any other model or drug or disease. And so here you start seeing where the power of, again, Pumas comes in, where you can use all these different features together. We're talking visualization, plotting, simulation, Bayesian estimation, writing your own functions in different ways, even logging, right? And they all come together to help you achieve or answer specific questions. For example, what is the best dose to give to a subject? So that's a specific question that we were trying to answer here. And you see that all of the features that you need are all here provided, starting from, again, the defining your data, reading your data, writing your model, estimating it, diagnosing your model, did it fit, did it not fit, etc. And then also simulating post-processing and defining arbitrarily complex simulations and decision-making exercises. So yes, so I think with this, I will conclude the warfarin dataset example. So any questions? Okay, so let's see how we're doing on time. That's the DeepPumas workshop. We'll come to that in a second. So we took a little bit too much discussing this, but because we also discussed a little bit of Bayesian estimation from yesterday. So technically, we should be touching upon tumor growth dynamics before the break. So the break is due in about 15 minutes. And people mentioned that we want to switch survival modeling and introduction to DeepPumas. So I'm going to do that, but before the break, maybe I'll take a chance to just quickly go through the tumor growth dynamics part of the tutorial, and even maybe briefly cover survival. And then at the end, we can, after the break, we can come back and discuss some DeepPumas. So if there are no further questions about this warfarin case study, I'm going to conclude it and move on to the next one. Okay, so let's do that. So the second case study for the tumor growth dynamics and overall survival case study is in this second folder, TGDOS folder, and it's you need to open this file, tgdos.jl. Now let's take a look at this real quick. Now, since we've already seen a reasonably complicated sort of case study with the warfarin data sets and optimizing doses and so on, this should all look very familiar now, so hopefully nothing here should be too surprising. So the first step is I'm reading the data set again into this data frame. So I'm loading Pumas and all these other packages, which I think have already been loaded. So yeah. And then I'm double checking that I'm still in the correct folder, which is in my case, I would like to be in this top folder here. And then I'm reading the data frame, and this data frame, I'm passing it all the missing string annotations. So if it sees a dot, it's going to treat it as a missing. If it sees an empty string, it's going to treat it as a missing. And just to quickly inspect whether it correctly identified missing values or not, weight is float 64, good. Sex is a string in this case. And then SLD is a missing or a union of missing and float 64. And death here, which is the event. So this is an event that implies if it's 1, then the patient died at this time point, and if it's 0, then the patient dropped out of the study at this time point. So that's this death or censored, essentially, event column that we have here. And then SLD is the sum of longest diameters, which is the tumor size measure for any kind of tumor, basically, and this is the observation time, and this is the subject ID. But you see that all the correct, I think, the correct types are there. So that means hopefully we captured all of the missingness here. Okay. There might be a risk, for example, that there's a missing value here that was not captured, because you never know with strings. If there were missing values that were not captured, it would also be read as a string. So you never know, but I think we can assume that they were all captured in this case. Now, next, I'm going to call the read_Pumas function. And the read_Pumas function is what we used last time. Again, you pass it the data frame, and you pass it. So before, if you remember the warfarin, we actually passed it a whole bunch of things like ID and time and AMT and compartment and so on. Because ID and time in the data set or in the data frame are lowercase, I can actually drop this. So in Pumas, we use lowercase ID and time. And so I don't need ID and time here because they're all already there in the thing as lowercase. And so if I do it like this, I can also pass it like this, but it's redundant. If it's already lowercase, then it will just pick it up automatically from the data. Because that's here. And so all I have to do is now pass it the observations. So there are 2 observations. One is a continuous observation, and one is a sort of a binary observation, which is a death event. And then the SLD, which is the sum of longest diameters. And then for covariates, I have the weight, age, and sex as covariates. Now, if you also look at here, we have this compartment and EVID and even amount. So I need to pass all of this unless I set event data equals false. So if I know that there is no dose being provided or there's no dosing data at all, then if I set event data equal false, then I don't need to specify what's amount and what's the compartments where those goes in and all that stuff. And so this is an easier way to define this data frame here or data set. Instead of adding all these dummy columns, I don't need them because there's no dose or no event data in my data set. And so I'm going to call the read Pumas function like this with event data equals false. And then this here is the tumor growth and overall survival model. And perhaps the main difference that we see here is that we haven't seen this vector domain before, I believe. So a vector domain is just like a real domain, but it's for vectors. So it allows you to define a parameter that has two values or two dimensions instead of just a scalar or a single number. And you can give it initial value here, for example, 1 and -1. So this beta here will be a vector of length 2. And then there's another domain here called PSD domain, which allows you to define a domain of all positive semi-definite matrices. So omega here will be a dense positive semi-definite matrix. In the warfarin case study, I think we use the diagonal domain here, or p-diag domain. So here it was only a diagonal covariance matrix, whereas here it's a positive semi-definite dense covariance matrix. And then I have my sigma, which is the residual error for the sum of longest diameters. So here I'm actually defining a joint tumor growth dynamics and overall survival model. And so I'm having, this is all the TGD model parameters, and this is all the survival model parameters over here. Again, nothing surprising so far. We've seen most of this stuff before. Then we have random effects. Again, the random effect eta is defined as a multivariate normal with mean 0 and covariance matrix omega. Omega is coming from here, and this is a 2x2 matrix. So it's actually able to capture the dimension directly from the initial value that you pass in here. So you pass in here this initial omega, and it knows that this is a 2x2 matrix, positive semi-definite domain. And so omega will be a 2x2 matrix here, and we have two values for etas. So we have two random effects per subjects. Okay, and this here is the list of covariates. Here I'm showing you that you can also do it on multiple lines, or you can do it on the same line like this. Both of these are going to be valid. So I think last time we showed it on a single line, but you can also do it on multiple lines. And then here I'm just defining the log logistic hazard function here, which is defined like this. So it takes this specific form. This is the log logistic hazard. As a function of time and as a function of the parameters that we defined. That's a pretty standard hazard function. And then H here is where the covariate model comes in. So H has the H0 parameter, but then also has the covariate model coming into here. And the covariate model has things like the baseline covariates, like age and sex, but also has things like the tumor itself. Is that... Actually, no, the tumor is not going here yet. Or it is. M is actually supposed to represent. Okay, so we're going to be using M as the mean SLD here. So this is going to be, let's say, mean SLD. And so M is also coming in here as well. And it's being used at the end as well as the mean SLD, right? And so the sum of longest diameters will be distributed with a normal distribution with this mean and this standard deviation sigma. Okay, and so we have this M or mean SLD that's defined here as a very simple function of time. So it's a linear mixed effects model of time, essentially, where we have this, the only input here is time, and the slope and the intercept have a population parameter and a random effect associated with them. Other than that, it's just a simple linear function of time, right? So it's the simplest kind of tumor growth dynamics model you can come up with. And sex here, here's how we show that you can actually use this. We've shown this ternary operator before, which is like an if statement. So if this is true, it will be 0, and if this is false, it will be 1. So this is just a binary encoding of the sex covariate, and this shows you that these covariates here actually don't have to be numeric covariates. So this could be strings as well. And as long as inside you handle it correctly, so here we're handling it correctly by checking which string it is, and then using the correct numeric representation of that, then it should be okay. And this is just the hazard function again that I'm defining here. So this is the instantaneous hazard function, lambda, and then I'm defining the cumulative hazard, which is just the integral of the instantaneous hazard over time. So if you're not familiar with survival modeling, I do have a few slides on in this workshop here at the end about survival modeling, which I can go through in a minute. Okay, beyond that, now we need to define the error models or the distribution of the data. So SLD will be distributed according to a normal distribution with mean given by this mean SLD and standard deviation given by sigma, which is the parameter sigma here. And then death will be, which remember is a binary, this is a binary response. When it's 1, it means that the patient died. When it's 0, it means that the patient dropped out of the study at a specific time point. And so for the rest of the time points, it's going to be missing. And so the way you actually define this time to event model, essentially in Pumas, is to use this time to event special distribution that we define, or special struct. And then the time to event struct here takes 2 inputs, takes the instantaneous hazard, lambda, and then takes the commutative hazard, which is coming out of dynamics, this uppercase lambda. And so these are the 2 inputs of the time to event. And this allows you to compute the log likelihood, essentially, of both events, whether it's a death event or a censored event, or a dropout event. And so the log likelihood will be defined slightly differently for both of these events. But all we need to define the log likelihood is these two numbers here at the time of death or at the time of dropout. And so this is a very simple joint tumor growth and survival model in Pumas. Yeah, my understanding is it's a lot less simple in some other tools out there. But in any case, so this is actually this demonstrates one nice feature of Pumas that maybe is worth highlighting, which I did highlight at the beginning. But the fact that we can define these distributions to mask all the complexity of calculating the log likelihood. So often you'll see a lot of non-MEM models where people want to define their own distributions, and they're writing the log likelihood calculation directly into the model. And these models tend to be quite unreadable in many cases, and you need to sort of work hard to figure out what's actually happening, especially if you send it to somebody who's not familiar with the model. But in Pumas and in Julia in general, we try to use these abstractions like a distribution abstraction to essentially define the behavior of a distribution, how to sample from it, how to calculate the log likelihood from it, etc. And then we can just use the distribution here directly. And this makes the model a lot more readable and also makes it easier to test, for example, this distribution first outside. Make sure that it passes all of the tests that can make sure that the calculations or computations are correct, and then we can just use it directly here. So that as a modeler, you don't have to maybe think too much about the math of the log likelihood every time you see the model, but only think about it once, or let us think about it and define the type for you, and then you can just use the type here. So an example that I did recently actually was a bounded integer model. So the bounded integer model, we defined a special type for a bounded integer. It's not yet sort of part of the release, but it was done internally by one of our, in one of the projects that we did. So you can use it for bounded integer models. You can use it for a combined uniform binomial error model. So you can do all these sort of crazy distributions or implements all these crazy distributions and then use them directly here, essentially. Now, the catch is that whenever you define these custom distributions, it's unlikely that FOCE will work for them. And if it does, then we need to generalize the implementation. So it will not just work out of the box. And so once you do these custom distributions, then you need to use Laplace for the fitting or for the estimation. Or obviously full Bayes also works. So you can do full Bayesian inference on this as well. And so in this particular model, because we have one Gaussian response and one time to event response, we cannot use FOCE, and we would have to use Laplace for fitting this model, or full Bayes. And so let's go ahead and actually run this model. And what I'm doing here is I'm doing a training validation split, and this is sort of creeping into a little bit into machine learning practices, where I want to keep some of the population aside for validation purposes. I don't want to use all of the population for training. And so what you can do here is just take the length of your population, multiplied by 0.8, for example, to get 80% of the number of subjects, and just round it to an integer. So this will get approximately 80% of the number of subjects here. And then I can use the indexing notation just to get the first 80% roughly of the population here, and use it to calculate the log likelihood. In general, when you define a model, it's always recommended to call the log likelihood function first, just to make sure that it's not giving you infinities or errors or something like that before you call fit. And the log likelihood function takes in as inputs the same inputs that a fit takes, which is the model and then the data and then the parameters, and then the Laplace I. So this is the equivalent of a max eval equals 0 in non-mem, for example. And maybe while it's compiling the model, you can just take a look at the fit. There's nothing new here. Again, just pass it the model and the data and the initial parameters and algorithm. And then at the end, if you want to calculate the validation log likelihood, I'm just taking all the remaining subjects here that were not included in the fit. So in the fit, we only included up to n subj. And here I'm taking all the way from n subj plus 1 to the last subject that we have, and I'm calculating the validation log likelihood, which I can then go ahead and use for model comparison. For example, if I have two different tumor growth dynamics models or two different survival models, and I want to compare them, one way to compare them is using this training validation split, where you compute the log likelihood and validation data that was not used to train the model, and then use that to compare the two models. And I believe I need to stop now because of the time. The break is due in 1 minute. So I'm just going to go ahead and run the fit in case we want to use it later. And now we can maybe receive some questions. And if there are no questions, we'll go on a 15-minute break, come back and discuss some machine learning and DeepPumas. Okay, so if there are no questions, then we meet again in 15 minutes. So thank you for your attention. Okay, so before the break, we stopped at calling the fit here, and you see that the fit has converged in 72 iterations. The gradient norm is pretty small, and the objective function has been minimized. The log likelihood value is shown here, and these are all the parameter values that we have. And then with those parameter values, we can get them using the COE function and then call the log likelihood function to get the validation log likelihood, which I can, for example, use to compare different models, or you can use obviously also commonly AIC and BIC can be used for this. But when you have large machine learning models, often AIC and BIC are not appropriate to use for model comparison, and you actually want to use this training validation split to more accurately estimate how does your model generalize to unseen data, which AIC and BIC try to quantify, but with making a lot of assumptions. You can also, if you use full Bayes, you can use things like WAIC and or the leave one out cross validation method to also get some estimate of sort of like an information criteria like measure that can be used. So there are many different ways to compare models, but we won't be able to go through all of them today. But maybe enough with that. And I think we had some popular vote earlier to try to discuss machine learning for the rest of this workshop. The rest of this file here is, maybe let me just briefly walk through it. It's actually a workaround because we currently we can fit a joint tumor size and time to event model, but when simulating from it, we actually are not able to do that, unfortunately, for many of the diagnostics and so on. And so what I'm doing here is I'm doing this max eval equals 0 trick, or iterations equals 0 trick, where I'm using the same fitted values of the parameters, but with just a TGD component of the model, essentially, rather than the whole model. And only the TGD population as well. So leaving out the death event and so on. So the rest of this file is just showing you how you can continue the rest of the workflow, including visual predictive checks and simulations, and for both the tumor part and the survival part. And so it's hopefully somewhat self-explanatory now that I explained why we're doing this. So we're just dividing the population or reading the survival part separately from the tumor parts, and then doing the rest of the workflow like this. Okay, so let's see. Now, I had not initially planned to discuss a lot of machine learning in this, but the initial plan that I had was to go through some of the introductory tutorials that we have, and hopefully that also shows you how you can find out more information. So if we go to our main webpage, pumas.ai, and then resources, and then tutorials here, And then you go all the way to the bottom, you'll see DeepPumas over there. And so we have three nice tutorials that were written by some of my colleagues. I did not write these tutorials. And they give you some idea about DeepPumas. But before that, let me maybe walk you through some slide deck first to explain what exactly are we trying to do with DeepPumas. And let's see. So this is a slide deck that was prepared by my colleague Nicholas Korsbo, who will also be giving a DeepPumas workshop, by the way, at Page. So if you're going to be in Page, you can stop by his workshop and get a nice 2-day exposure to DeepPumas. Hopefully, it will be efficacious. So the idea of DeepPumas is that we're trying to combine machine learning with traditional modeling, and I'm calling it here loosely scientific modeling, but it doesn't always have to be scientific in that it's mechanistic modeling, but it often is. In pharmacometrics, we often have mechanistic models. These can be nonlinear mixed effects models that encode the dynamics of how doses or how the drug affects the body in different ways. And the nice thing about it is it encodes the scientific understanding, like our scientific understanding, into the model directly, and any known hierarchies, for example, the fact that we have population parameters and individual parameters, etc. And this actually gives us a nice advantage, because the first advantage it gives us is data efficiency. So the simplest example is if I know that my function is linear, then all I need is 2 points to learn the function, right? So I only need 2 data points to learn that function. Whereas if I don't assume that it's linear, and if I assume that it's some complicated neural network, then it will take me many more points to discover automatically that it's linear. So when you encode structure in your model, or when you encode scientific understanding into your model, you automatically make your model a lot more data efficient. And that's the nice advantage that comes along with that. Of course, the disadvantage is you have to be right. Otherwise, you're making the wrong assumption. And so if you don't know exactly what the scientific model should be, and if you don't know exactly what the function should look like, then that's where empirical modeling or machine learning. So machine learning is just sort of empirical modeling reinvented in many ways. And so that's where the people resort to things like semi-empirical modeling or just purely empirical modeling. And many models used in pharmacometrics or nonlinear mixed effects models are actually not purely scientific. They're not all very scientific. For example, this Emax structure, sure, it's based on the saturation behavior that we observe, but the specific functional form, the Emax, there are many possible saturating functions, but we use this specific one, and that choice may be more just because it's simple, because it makes sense, it's easy to interpret. But there might be other functions that also have a saturating behavior that we chose not to pick, right? So there's we assume that the function is monotonic, for example, it goes in one direction only, etc. And so there's a lot of these assumptions baked into your model that may or may not be verified, and we assume that this is sort of a scientific model, but if you actually honest about it, sometimes you'll see that some parts of this model, like maybe the causal structure, is indeed based on scientific hypothesis, like the drug affects the PD or PK affects the PD in some ways, but the specific functional form took some trial and error, basically, to figure out, and it's not all based on just pure scientific theory. But regardless, we typically call this kind of modeling scientific modeling. Let's call scientific or redefine scientific modeling as any model defined by a scientist after some thinking about the problem. And so even if it's slightly empirical, we still like to use these models because they make sense, they can be easily interpreted. And so that's the second advantage, is that they tend to be, they have very few parameters, easy to interpret. We know exactly what's happening. We can pull out the function and test it in different ways, try different inputs, etc. And building confidence in the model and building all of this transparency and interpretability allows you to build confidence in your model, so that when you go to the regulatory agency, the EMA or the FDA, they look at your model and they see the parameters, they see that it makes sense, it fits the data, and then they're more willing to trust that your model can be used for dose optimization. And dose optimization is often involves things like either extrapolating to doses that have not been tried before, or even interpolating between wide dose intervals, which is also very difficult to do. If even if you're interpolating, but you have wide gaps, for example, in your data. And so any kind of interpolation or extrapolation requires confidence in your model, that your model is actually capturing something or the underlying dynamics. And this is why it's important to build confidence. And so interpretability, scientific understanding, all of those things are basically how we sell our models to the users of the models and the regulators, saying that this model makes sense, it fits the data, and we should use it because it's better than guessing. And it seems to be giving us good predictions. And of course, not every model is going to work well all the time. So maybe you develop your model on some data set from a phase 3 trial, but then if you try to use it in a hospital for personalized medicine, you might be surprised in that some of the patients coming in are different from the patients you assumed. And so like just because your model was scientific or was fitted on some data that was observed from a clinical trial does not necessarily always mean it's going to work for everybody or it's going to fit everybody equally or equally well in the real life, right? And so, but again, we still, this is the mechanism that we have now for approving drugs and for making decisions, which is based on scientific modeling. Now, for machine learning, it's a lot more sort of like a Wild West situation where anything goes in terms of the model. So the models used there tend to be extremely over-parameterized. So you can use like millions of parameters in your model. In some sense, so this also provides you some advantages, but some disadvantages. So the advantage is that you don't need to be right, or you don't need to guess a lot of the things that you don't know. And so you can, for example, say that, okay, I know that Y depends on X, but I don't know exactly how it depends on X, and I don't need to look at the data and try to guess how. I can just give it to a machine learning model, and the model can tell me exactly how this dependence looks like. And this in some ways gives me a lot of flexibility, so I don't have to keep guessing if there is no way for me to really know for sure what the functional form is. But it comes with some disadvantages, which is that like even though it can handle or find some unintuitive relationships that maybe I would have never guessed, or handle complex data, because as like you have let's say if you have hundreds of covariates or biomarkers or images or like omics data or something like that, it's unlikely that you will be able to look at the data, visualize it, and then figure out this is the scientific model I need to use. And so you're probably also limiting yourself when you only stick to this kind of modeling to very simple data that you can easily reason about. But with machine learning, it can look at image data, scan data, etc., and it can still try to figure out or extract patterns from this data and see how it exactly can be used to improve your model. And so figuring out these non-intuitive complex covariate models and automatically discovering dynamics or any kind of relationship between an input and an output is something that machine learning can excel at. Now, the disadvantages are that it lacks scientific understanding. And that's I give you a neural network, it fits the data perfectly, but then how do we actually make sense of this? How do we explain it to a regulator? How do you explain it to a clinician in a simple way? And so often the scientific understanding happens after the fact, and maybe calling it scientific is a bit much, but the understanding, at least, or trying to explain rather than understanding, trying to explain what the model is doing, happens as a post-processing step. So you find the neural network, and then maybe you visualize it, you plot it, you do some sensitivity analysis, you figure out what happens if I increase the exposure to very large values, very small values. Does it still give me something reasonable or not? And then you can go back to the model if it's not being reasonable, and then you can try to build more assumptions into your model. So even though a machine learning model is an empirical model, you can still try to build some assumptions, like, for example, the asymptotic behavior that you have with many of these exposure response models. You can still try to build them into your empirical model, right? It's just that you need to be more careful now, because anything can happen, and you're not able to see the behavior of the function just by looking at it, and it's often a complicated function. And so it requires a bit more scrutiny, let's say, to fully trust that the model is actually working correctly. Another disadvantage of machine learning is, as I said, it requires a lot more data, especially if you already know what the structure is and you're not using it. Then you're really wasting a lot of resources here, because if I know that the relationship is linear, I should say that I should encode the linearity assumption. Otherwise, I would be requiring a lot more data to discover this bit of information. And so pure machine learning models, they tend to require much more data, or they're more data hungry than scientific modeling, because again, the functions themselves are so flexible that to figure out which function should be used, you often need a lot more data to help you with that selection process. And inscrutable is sort of because, again, unless you try to sort of dig into it a bit more or do some sensitivity analysis, the model itself does not lend itself nicely to like some people reading it or people making sense of what it's doing just by looking at it. And so the hope is that we can combine both of these sort of two worlds together into this, what we call scientific machine learning. So you'll find this name floating around, or this term floating around a lot in pharmacometrics, but in the literature in general. But basically, the way we use it is that we're combining elements of machine learning or empirical modeling with scientific modeling. So it's just a fancy new name for semi-empirical modeling, essentially, where we try to combine both scientific and machine learning components. But the machine learning, we hope to be able to access things like neural networks and complex machine learning algorithms, and not just simple, for example, like linear or polynomial regression or something like that, which some people would still call that a form of machine learning. But we hope to be able to use more complex machine learning. Good. And so the goal of that is that we can hopefully make good predictive models. So even though I said that these machine learning models might be not very interpretable, might be difficult to make sense of the model and the parameters and what exactly it's doing, but it tends to be very, very good at prediction usually. And so the predictive performance of machine learning models tends to be quite good. You know, of course, it's going to be better than an incorrect scientific model, but it's not going to necessarily be better than a correct scientific model. So if you actually know the scientific mechanism, but still, nevertheless, we usually don't know all of the mechanism in biology anyways. And so what we suggest to do is to use this machine learning, add it to your scientific modeling to help make it more predictive, improve its predictive performance, to help learn structural equational or certain forms or functional forms that might be difficult to guess, use machine learning for that. The opposite of that, you can also look at it as the opposite, where we are starting from machine learning and then encoding our scientific understanding one step at a time into our machine learning model. All right, so you can go at it from either direction, either start from scientific modeling and incorporate machine learning into it, or start from machine learning and incorporate scientific modeling into it. Eventually, you reach a hybrid model that has a bit more or some scientific components and some machine learning components. And again, the hope is that we're able to make good predictions at the end, but also we still have some scientific understanding built into the model, so it's still somewhat data efficient and it's not extremely data hungry. It will definitely be more data hungry than a purely structural model, but the hope is that you're getting a good trade-off between data requirements and predictiveness. And also being able to use all these complex covariates to improve the prediction of the model. So things like medical images and omics and even text, like, you know, people writing text, and you know, all sorts of like maybe molecular interactions or graphs, like the molecular representation of the drug itself. So data that might be, again, difficult to use directly in your model, but might still carry some information that might help. For example, things like biomarkers, things like images, etc. And the hope is that we would like to use DeepPumas across all of the drug development and healthcare sort of sections. So whether it's lead generation or clinical research or market research or even manufacturing and patient management and individualized medicine. And so this approach really lends itself nicely to many different applications, but we showcase only a few here. And so everybody here already knows nonlinear mixed effects modeling. So let me show you a flavor of scientific machine learning, which combines sort of this traditional scientific model. So this is a sort of PK model. Very few people probably use like PK models. They tend to be limited, and we only try a few of them. But that's just to demonstrate how we can probably bring in some machine learning here. So let's take a look at this PK nonlinear mixed effects model that has two covariates, age and weight. It has the typical values or the population parameters, theta and population parameter omega, which is used to define the random effects distribution prior as a multivariate normal. And then we define the absorption rates, the clearance, and the volume for each subject. And then we define the dynamics here with one depot compartment where the dose comes in and one central compartment. So it's a very simple PK, single compartment PK model. And then we have here a proportional error model at the end for the for the error model. And so again, very, very traditional, very simple, but it encodes a lot of understanding, even in this very simple model. In fact, we have a covariate model here that we also defined, right? So it encodes the understanding that we have a population of subjects, and we do have some shared parameters between the subjects, and we have some individualizable parameters, which are all the etas here, or the random effects. It encodes the covariate effect that we know that age might affect absorption, and weight might affect the volume of distribution. And so there's a lot of scientific understanding that's encoded here into this model. And then it encodes the fact that we know that the drug goes first into a depot compartment, so like the gut or something like that, and then it gets absorbed into central. And so everything that comes out of depot goes into central. Right, so this is another key assumption that we're encoding in here. We know that Ka is positive and that Cl is positive and V are positive. And then we encode that also we have some clearance. So the drug eventually comes out, and that the clearance rates or the clearance rate of change only depends on central and does not depend on depot. And so this is, again, scientific understanding that we just encoded into this model. And so all of this scientific understanding helps make the model easier to fit with less data, with more sparse data. But let's say we don't actually have all of the covariates, like we didn't use all of the covariates here, we only used 2. And we have a lot more covariates that we can use, and so this is where machine learning can help. Now, the way to think of or the specific instance of machine learning that we're going to sort of use here is a neural network. And the neural network is basically just a universal approximator. So this is supposed to be a video. So let me see if I can... I don't have the slides here in a PowerPoint format, but basically it's a universal approximator that tries to approximate any function, and it's loosely based on this idea of neurons in the brain, but it's just a bunch of nonlinear functions stacked on top of each other. So it's just a very complicated function with a lot of parameters. So think of it like fancy polynomial regression, right? Which again is extremely flexible, has a lot of parameters, and can easily fit any kind of functional form. But at the end of the day, it's just a function. And so the way we're going to bring in this function is into, literally you can do it anywhere in your model. And so we can, for example, bring in this neural network into this part of the model to define some covariate model that to capture the dependence, or to have input here, for example, an image, input here baseline biomarkers, or a lot of other covariates that we did not know how to use ourselves. But then let the neural network figure out how to use all these covariates to affect the absorption rate to then eventually fit the data better. And so we still don't throw away this whole part of the scientific model, and we're just recalling the neural network to help us only with this part of the model to, for example, define a covariate model or a better covariate model. Another part where we can use a neural network is maybe in some part of the dynamics. I said it's just a function. Previously, we assumed that clearance is just linear like this, or the clearance rate of change is just a linear function of central. But maybe it's not linear. Maybe for some drugs, it's a lot more complicated, the clearance profile. And we don't actually know what the functional form of clearance should be. And so we could actually replace part of the dynamics itself with a function. And this function could take as input central. So it could have only one input, which is central. And then, so we're telling it that the clearance rate only depends on central, and we can force it to have a positive output at the end. So we're forcing it to have, again, a positive number at the end. So we can encode some basic assumptions into this neural network, but then otherwise leave it free to do whatever it wants to fit the data. And so otherwise let it figure out what is the best way to utilize central, or what is the best functional form that it can discover to fit the data in the best way it can. And so once you think of a neural network as just a function, now it becomes easier to see that we can throw it anywhere in the model. In fact, another place we can throw it in the model is in transforming the etas. So before we use the random effects here, we can transform it with a neural network. And what this is equivalent to is it allows us to use arbitrary distributions, essentially, or to learn the random effects distribution and no longer assume that it's just a Gaussian. So it could be a Gaussian and then transformed by some arbitrary nonlinear function, which allows us to capture some complex distributions here for the random effects. And this is sort of the main idea behind the work of my colleague here, Lorenzo Contento, who presented it in a webinar a couple of weeks ago, where he shows a much more efficient way, essentially, to do the same thing, which is reparameterize our random effects distribution, but in a more efficient workflow, and using something called the normalizing flow, which is a special neural network based model. And so The idea is that we can throw a neural network anywhere in here. We can throw a neural network here, for example, to maybe encode the relationship between drug and pain score. We can use a neural network in discrete data models. We can use neural networks in many places here. Or we can completely just rely on neural networks. So if we want, we can also remove all of the structural knowledge and just use a pure machine learning. So you have the full spectrum of things. You can do full scientific modeling. You can do full machine learning with a neural ODE, for example, style model where we have all of the dynamics are explained by a neural network. Or you can do somewhere in between where you have a model that works maybe, almost perfectly well, but not quite there. It has some limitations. The diagnostics don't look great. The IPRES versus observations are not the best. The VPC is not the best. And so you use a neural network to try to enhance your model in any of these ways, whether improving its individual predictiveness, improving the distribution, or learning a better distribution of random effects to improve the VPC, or just to discover a better model in general. And once you do that, the nice thing is you can then take these neural networks out and try to reason about what they're doing, trying to explain them in different ways, figure out, are they actually using all of the inputs that you provided, or were some of the inputs redundant and not useful? And so you can then try to query the neural network afterwards and see what the functional form was that it discovered at the end. And then if you want, you can then go ahead from there and try to guess what the functional form is. So if you really want an analytic solution, you can try to guess what the functional form is. We've also experimented with something called symbolic regression, which after we fit the neural network, we try to figure out what's a good symbolic representation of this neural network that's a lot more compact and human readable. And we've had some success in some cases, but not so much success in other cases. So it's quite finicky to figure out what's a good functional form. But you can always plot it and take a look at it and see what it looks like. Good. So as I mentioned, the inputs to the neural network can be anything you want it to be. It can be the covariates, it can be dynamical variables if you use them inside the dynamics. You can even have random effects as inputs. And this actually is the basis of my next talk, which is that nonlinear mixed effects models and generative machine learning are the exact same thing. And that's because generative machine learning also uses the same concept of random effects. I'm not going to spoil the talk too much, but the idea is that you can actually generalize or read like the same models that we write or that we can write with DeepPumas and even with regular nonlinear mixed effects modeling are technically also generative machine learning models if they're empirical and if they use random effects. And I'll talk more about this relationship in my webinar in the upcoming few weeks. But yeah, the idea is that you can pass in random effects as input to individualize the output of this function. So every output, for every subject, you might have a different output, even without covariates. So even if you don't have covariates as input, you can still individualize the output of the function for each subject by having random effects as input to this function. You can also have time or, like dose or whatever it is that you want to input here. And so there's really a lot of flexibility and a lot of different ways to use these neural networks. And we've had a lot of success with different applications of this in various projects. And so, for example, we've had some reasonable success with extracting features out of images and trying to use them to inform different parts of your model, or defining some complex PKPD model or part of the dynamics using a neural network. And so even discovering some random effects distribution from like a multimodal, like you have data that's multimodal and you don't know what to do with it. For example, in tumor data, you often have responders and non-responders, and sometimes you would need to use a mixture model, for example, to capture this multimodality. But instead of that, you can also use a neural network to try and learn the distribution of the random effects without having to resort to mixture modeling. And it's also a lot more flexible than mixture modeling because it can handle multimodality, but it can also handle nonlinearity in your distributions of random effects. So the hope is that we try to bring in sort of the best of all of these tools together. And so pure machine learning lacks scientific understanding, dynamics or like the scientific models that we develop, which are typically dynamical models, they tend to be somewhat inflexible. And then the statistical nature of the models that we have is often essential because it helps us encode, it helps us like be more efficient in our learning by sharing some parameters between subjects so that we don't have a separate model for each subject, for example. No, we have a hierarchical model that shared some parameters between subjects that allows us to do information sharing. So some subjects can have sparse data, some subjects can have dense data, but we can still learn the overall population trend. And so this is also a very important part. And the hope is that with deep NLME, or what we're calling deep nonlinear mixed effects modeling, is that we can combine all these sort of different components together in one software tool that lets you, it doesn't mean that you have to use all three of them. It just means that you have the option of. So you can do pure machine learning in the same tool. You can do pure dynamical and scientific modeling in the same tool. And you can just do regular statistical modeling even without dynamics in this tool. But you can also mix all three together. So it's a nice feature to have. So this is the overall idea of the DeepPumas, sort of from a high level. Now we can talk more about the specific details, but maybe let me see if there are any questions. Okay, so let's move on to the next slide deck. Good. So this is a slide deck that I don't think we'll be able to go through all of it today, but it covers sort of the this relationship between machine learning and well, it first introduces us to some basic concepts in machine learning and neural networks, and then it covers the relationship between machine learning and conditional or generative models that I was talking about earlier. This is a bit of a historical sort of slide that talks about some of the history of machine learning and neural networks. Actually, one of the founders of Pumas AI, Joga Goboru, had, I believe, his PhD was on machine learning, his PhD thesis, and he had a paper published on using neural networks for PKPD even as old as 1996. And so this is not necessarily a new concept in the sense that people have been trying to do this for a long time, but we believe that one of the main sort of limitations that stopped people from experimenting a bit more, beside the philosophical aspect of things, is the lack of good software that people can just use that's accessible to everyone. And so in many ways, when non-MEM was invented or was created, it did make pharmacometrics a lot more accessible. And as time goes by, even in machine learning, we have similar sort of breakthroughs with software tools coming out, like Theano initially in 2010, and then PyTorch and TensorFlow. And so software generally helps accelerate research. We hope that the release of Pumas was also another major milestone, and that it made pharmacometrics a lot more accessible compared to using non-MEM, for example, and being able to use or do all sorts of activities in one software tool. And we hope that the release of DeepPumas, which actually happened late last year, that it also marks a good milestone that we can then hopefully look back to in the future and say that this made machine learning more accessible in nonlinear mixed effects modeling and pharmacometrics. And so again, deep learning has already been, obviously, it doesn't need any introduction now. It's been extremely successful in many different domains. In fact, in healthcare and medicine, it's also seen a reasonable level of success with things like toxicity prediction, or just looking at images of maybe a skin disease or something like that and trying to classify it. And so there's a significant number of case studies that have successfully used machine learning and deep learning to help either diagnose patients or predict some properties about drugs and so on, using different inputs or characteristics. And so so again, machine learning does not need a lot of introduction, and it has seen quite a lot of success, for example, in dermatology. And this is here, for example, a machine learning model that can do almost as well, if not better, than some human dermatologists at predicting and labeling what this disease is just by looking at it. And so and hopefully these case studies show us that there is a lot of potential, especially with image data and complex data that might be difficult to just reason about as a human. And it takes many years of training, for example, to be a dermatologist. But if you feed the machine learning model a ton of data, then it's able to reach a similar level of predictiveness. Now, the CNN CNN doesn't know anything about dermatology, the science, but it can still predict pretty well. And so it's not the best model for understanding the science behind things, but it is usually or can be made into a good model for predicting things. And so that's where machine learning can mostly excel at, predictiveness. Now, broad types of machine learning. So we often have a different categorization of machine learning. This is sort of the short list. There are many other categories that keep coming up, but they're like generally speaking, there is something called supervised machine learning and unsupervised machine learning. And with supervised, the two main ones that we have inside the subcategories is prediction tasks like regression, whether it's linear regression or nonlinear regression, and then classification, which can be binary classification or multinomial classifications. You may have multiple categories. And so this is like logistic regression, for example, but maybe the nonlinear version of it. But some people would even call linear logistic regression machine learning. But supervised, what characterizes supervised machine learning is that you have some input and some output, and it's like every input point has an output point that's paired with it, and so I can have some input X and output Y, right? And Y here would be called the label, and Y would be, for example, the response, like the response variable, which could be a continuous variable in prediction or could be a discrete variable in classification. And then we have unsupervised machine learning, which there are many models in this category, but things like generative models, which just tries to learn the distribution of a data. So a generative model is just a fancy name for a distribution. So it tries to learn the distribution of the data by looking at the data directly. So there's no X and Y here anymore, like we have in prediction and classification. There's just data like X, everything is X, and we're trying to find what's the probability distribution of X, or learn some representation for this probability distribution. And the goal here is that we want to be able to simulate fake data. We want to be able to simulate synthetic data that looks like the real data. So there's actually a website, I think it's called This Person Does Not Exist or something like that, that was basically a generative model that was trained on a bunch of photos of people, many photos of people, and now it's able to generate fake photos of fake people that don't exist. Now that might be a mostly useless task, but it's maybe it's not that useless. Maybe it can be useful for advertisements and stuff like that. But again, the goal is of generative models is to learn distributions of data, not necessarily to predict Y given X, for example. We can also do feature extraction. So feature extraction is like a model that can, for example, you feed it an image and it tries to extract a vector of numbers. Those vector of numbers represent some important features about this image. And then you can use those vector of numbers then to reconstruct the image if you wanted to. And so you can figure out a model to sort of extract this feature vector, and then another model to decode or so the first step is often called encoding, and the second step is often called decoding, to decode this feature vector and generate the image back or get back your image. And so feature extraction would technically be considered another unsupervised machine learning task, because you just feed it some data and you try to essentially reduce the dimension of this data. So another often term that's used synonymously with this is dimension reduction, where you try to reduce the dimension of your data by extracting only some key features from the data. So something like principal component analysis, for example, would be falling in this category. And then clustering would be another unsupervised machine learning task. So these are all often called tasks in machine learning. So machine learning is divided by tasks, and the task just involves it's sort of the smallest unit of like the objective. Like you have your data, you have your objective, you have your model structure. This can be used to define a task, like a certain goal that you have in mind. And so clustering here is another task, and the goal here is to give in some data. So I give you a whole bunch of points, plotted around maybe two-dimensional points, and then the goal is to cluster them or to divide them into clusters. And so you can think of this as a way to just figure out, for example, like if you have the retail business and you want to figure out how many types of people do you have in your how many types of customers do you have. Maybe some people they buy a lot, some people buy less, or in the pharmacometrics case you have maybe responders and non-responders, and so maybe different people respond to drugs in different ways. attendees. And so before even starting your analysis, you can use clustering just for exploratory data analysis, just to look at your data. If you have a large data set, it might be difficult to visualize every single subject. And so maybe you want to first cluster the subjects into maybe 3 or 4 clusters, or whatever number of clusters that the machine learning tells you is appropriate by some measure of appropriateness. And then take a look at only the clusters and see where the most of your trends are, or most of your patients are in these clusters. And so clustering is another unsupervised machine learning that, again, you feed it the data and it gives you some function of this data, essentially, at the end. Now, clustering can also be seen as just discrete feature extraction, essentially. So you're extracting the cluster is the discrete feature that you extract from your data. And so for every point, it will have a cluster associated with it. And then we often have mixes of these in different ways. And so you can have semi-supervised machine learning. There's something called even self-supervised machine learning, which first does clustering and then uses the cluster as the category and then does classification on top of that. And so there are all sorts of mixing and matching of all these different methods, and they have applications in various areas, but they are definitely underexplored in the field of pharmacometrics, where people typically just do maybe one task like prediction or covariate modeling or something like that. But there's a lot more potential to exploit many more machine learning techniques in pharmacometrics. But for example, one other way to combine them is to first do feature extraction and then use the features that we extracted to do classification. So this can be useful for images. For example, if I have images, I can extract features from the images and then it gives me a vector of numbers. And then I can use this vector of numbers as regular covariates in a nonlinear mixed effects model, or to help me with classification or to help me with prediction. All right, so you can combine these in different ways and you get something that's loosely named semi-supervised machine learning. Good. Something else you can do is that instead of having a generative model, you can have like that just learns the distribution of your data. You can have a conditional generative model that learns the distribution of your data conditional on some covariates. And so maybe I want to learn the distribution of male photos and female photos separately. And so given the sex, I want to generate a different distribution of faces. And so the generative models here can also be conditional on some covariate. And so I can still have an X and Y, and that could also be loosely called semi-supervised because it has some components of both. Although these terminologies, supervised and unsupervised, tend to be less useful, and semi-supervised and self-supervised, and again, there are many other categories like this. These tend to be less useful, and it's more useful to focus on a specific task. Like, what is a task exactly? Is it a prediction or classification, or am I trying to learn the distribution? Is it conditional on some covariates or not? Am I trying to extract features or cluster data, etc.? So focusing on the task is often more important than what you want to call this task at the end. Another field of machine learning that's not very also well explored yet in pharmacometrics is reinforcement learning. And this is basically using machine learning for sequential decision making in any stochastic environment. So one of the breakthroughs in reinforcement learning happened when with the AlphaGo project. The AlphaGo project was a machine learning model, is a reinforcement machine learning model that was able to play a game called Go, which is a sort of much more complicated version of chess that's often played in I believe China, Korea, and many Asian countries. And Go is a very complicated game that had, I think, the world champion was Korean, and Google developed this, DeepMind developed this algorithm that was able to beat the world champion of this game. And so this is also very interesting, but you can think of, instead of a game, it's any stochastic environment where, let's say, you give a certain dose to a patient, and then the patient responds in some ways, and then you have to adjust the dose based on that. And so adapting the dose with reinforcement learning, I've seen a couple of works on that as well, but it's definitely not sufficiently explored yet, in my opinion. But also this is not within the scope of this workshop. Or rather, like in DeepPumas, we haven't yet explored reinforcement learning in DeepPumas. So just some general notes that not all machine learning, just keeping an eye on time, not all machine learning algorithms will use a neural network. So we have a lot more machine learning methods that do not use neural networks. Neural networks are just a subclass or a subset of machine learning, or just a tool, really. A neural network is just a function. It's a tool that's used in many different machine learning algorithms. And not all machine learning algorithms even use probabilistic modeling. So we will see that a lot of the focus that a lot of our focus as the DeepPumas group is on probabilistic machine learning models because they really fit nicely with the nonlinear mixed effects modeling. In that, like, you can have a unified view of both of these types of modeling. But it's always important to keep in mind that not all machine learning algorithms use probabilistic modeling. We have very simple algorithms like k nearest neighbors or decision trees or XGBoost, like XGBoost, which are based on decision trees often, and then things like hierarchical clustering or different clustering algorithms that also tend to not use any probabilistic modeling, but they still get the job done. And that's where the focus on the task is quite important. So in machine learning, the goal is not to develop a fancy probabilistic model. The goal is to do this task. And if you can do this task with any kind of heuristic that works, and that this heuristic has some hyperparameters and you can find the best hyperparameters, then this is technically machine learning. And so you don't have to necessarily use a probabilistic model. And so many of these are essentially heuristics that have some hyperparameters and that you can tune them in different ways. Good. Now, what people call probabilistic machine learning is in many ways similar to Bayesian statistics or computational Bayesian statistics. In fact, many of these topic or concepts from Bayesian stats have been reinvented and renamed often in probabilistic machine learning. And so these two terms are somewhat synonymous with each other. It's just that with probabilistic machine learning, we often use a lot more neural networks, whereas in statistics, people frown upon using any over-parameterized model, and there's a lot more emphasis on reducing the size of your model and so on. But in machine learning, there's no such frowning, and the bigger your model, the more excited people get. And so it's okay to use large models here. Machine learning itself as a field builds on many other fields, including, as I said, statistics already. In fact, logistic regression, linear regression can be considered one of the main bases of machine learning. Some people would call them even machine learning, although maybe I don't necessarily agree, or not everybody agrees, let's say. Optimization, because we need to use optimization to find the best parameters. Like, how else can we find the best hyperparameters or best parameters except with optimization? So we need some optimization methods for that. Database management, because if you have things like DBScan actually stands for database scan. So if you have large data sets, you often need to figure out how to store them in the most efficient way and how to access them in the most efficient way. So a lot of, so in machine learning, you often have to worry about the data, where it's stored, how big is it, what's the format of the data, etc. Even image and signal processing are somewhat predecessors to machine learning, and a lot of concepts from these fields have been borrowed into machine learning and computer vision and so on. And obviously, generally just software engineering, because with these kinds of complicated models and complicated data, you often have to write complicated software to manage the data and fit the models and find the best model and so on. And software engineering is an important part even of the history of machine learning, because, as I said, as software tools came out, it became more accessible to researchers, and then researchers could do more fancy things, and then the software kept trying to catch up with the research and vice versa. And so often some research will inspire software to come out, but then the software can be used by other researchers to do even more crazy things, and then that inspires even more software to come out and so on. Good. Some related terms to machine learning is maybe data mining. You may have heard it. In fact, I think data mining is often used to refer to some of these non-probabilistic models. So some of these would be studied in the data mining literature, but otherwise it's very similar. Data mining is about mining some patterns or digging out some patterns from your data. So these could be synonymous in some ways. Data science is, again, maybe a very general term that's often used to refer to much of this terminology that we're using here. Artificial intelligence these days is just a synonym for computer science, really. Anything under the sun can be called AI, although I guess maybe up to until LLMs came out, and now it's only LLMs that are AI. Now, but jokes aside, artificial intelligence is largely, again, any form of intelligence that's artificial, and that terminology is extremely general, so it doesn't really mean much most of the time. You probably want to talk more specifically about either a specific task or a specific algorithm, but AI is way too generic, and it's only a marketing term. Good. So I mentioned that probabilistic supervised machine learning is involves some data that's like input data X and output data Y, right? So that's the main sort of that's the task of often the task of supervised machine learning, which includes things like prediction and classification. So let's focus more on these two terms. And so X here could be a bunch of inputs, could be continuous, could be discrete. Y, if it's continuous, we call this prediction. If it's discrete, we call this classification. Or if the Y is categorical, we call it classification. Otherwise, we call it prediction. So you can still have like an ordinal Y, for example, and I guess you would call that prediction because it's not just it's not different classes, it's just a discrete score or something like that. And the idea here is that this model, that the model that we need to build is called a conditional model. So a conditional model is just a model with covariance. So that's another name for it. Another name for it is also a discriminative model. And so it's a model of Y given X. So given X, I want to predict Y. That's my objective. And I'm interested in a points prediction. I'm not interested in a distribution of Y, in just a single prediction of Y given X, right? So that's the typical task with linear regression, for example, or logistic regression if Y is binary, or Poisson regression if Y is ordinal, for example. Now, so these are all a bunch of prediction models, and even though prediction models, the goal is to just predict, often the way they're fitted assumes a distribution first, and so we assume some distribution and then we maximize the log likelihood, but at the end of the day we're only interested in the mean, and so we always assume that the sigma is like 1 or something like that, for example with linear regression, and we ignore it. But often the underlying probabilistic model is going to be a model that looks like this, where given an X input, we have f of X, a function of X, that gives us the mean of this normal distribution, right? And this essentially is the prediction of the value of Y, and then Y itself we assume is normally distributed around this value f of X with some noise. And often in the prediction, we're not interested in quantifying the noise, we're just interested in quantifying f of X. Now, if Y is unconstrained, then we use normal. We can use log normal if it's, let's say, only positive, in which case you can just do like linear regression, for example, on log of Y. So if f here is linear, then this is just linear regression, a linear regression task. If f is linear and sigma is 1. Right, and if f is linear here, then this is again linear regression, but on log of Y. So log of Y is going to be the response essentially. Now in classification, it's very similar, but now we have a bit more sort of ceremony here, where the output of f of X, because let's consider f as a linear regression function. If f of X here can output anything from -infinity to +infinity, how do I go from that to a category? And often what we do is we sort of do the logit transform of the category, and we try to sort of do like logistic regression, which uses the logit transform of the category. Or another way to write this is that we can call the logistic function on the output of f of X, and then we use this as essentially the probability distribution, use this as the probability of success or of getting the category 1. Let's say this is a binary response, then this would be the probability of getting a category 1 in a Bernoulli distribution. So a Bernoulli distribution is just a fancy name for a coin flip distribution with only 2 categories, and so there is always the probability is 1 parameter, which is the probability of getting one of the outcomes, and then obviously the probability of getting the other outcome is just 1 minus this. And so the logistic function gives us something that's between 0 and 1, and then for any kind of input between -infinity and +infinity. And so this works nicely because now we can use it as the single parameter of the Bernoulli distribution, and then this essentially is the underlying probabilistic model behind logistic regression. And your prediction essentially of whether or not you get a 0 or 1, or rather how much of usually you get a continuous prediction. So you can find, for example, the logistic of f of X. So for a new X, for a new input X, I can evaluate f of X, I can evaluate the logistic of f of X, and maybe if it's more than 0.5, I can say that I can predict that it will be 1, the response will be 1, and if it's less than 0.5, I can predict that the response will be 0. And so can use the mode here, the mode of the distribution, as my prediction, right? Or if I'm okay with a continuous prediction, then I can give you the actual number here directly. But if you want the mode, then we can give you the mode as well. And so, but the idea is that, again, it's loosely, or this is the probabilistic model behind it, essentially, behind logistic regression. Now, multinomial regression has another probabilistic model behind it, which uses this other function called softmax, which is like a multidimensional logistic function that allows you, that given a multidimensional input, so f of x now can return maybe 3 numbers, and then softmax will return you also 3 numbers, but the numbers add up to 1. So they're all positive, and they're all between 0 and 1, and they all add up to 1. And this is a softmax function here. And so again, it's a nice way to get these probability parameters that we can then feed into a categorical distribution to define our probabilistic model. And in a similar way, if you want to make a prediction, you pass a new x, for example, you evaluate these probabilities, and then you can find the category that has the highest probability, and that's your prediction. And so that's how you can use this probabilistic model to achieve your prediction task or your classification task. Good. Now, in probabilistic unsupervised machine learning, the goal is different. So here we don't have any labels or any response, and like we don't have inputs and outputs. Here we just have this data y, or you can call it x or you can call it y. And so let's call all the data here yi. So there's no input and output. It's all part of the output, essentially. And the goal here, for example, is to learn either complex distributions or data distribution or dimension reduction, as I said, or feature extraction or clustering. And so let's go through some of these tasks here and how we can achieve them with probabilistic modeling. So often with the same probabilistic model, you can achieve multiple tasks. So with one probabilistic model, you can achieve multiple of these tasks at the same time, or using different applications of the model. And so, for example, if I want to have a generative or learn the distribution of y, then I can directly try to figure out some distribution, so even like a basic normal distribution, and then learn the distribution of y, or try to find the best parameters that maximize the likelihood, for example, of the observations that I have. Alternatively, maybe I can define a model that has something called latent variables, which I will come to in a moment, and then define my distribution in a conditional way. But it's conditional on this random variable or on this latent parameter, essentially, z, that's also going to be estimated. So this is like an input to a function that we also try to estimate, but this input is assumed or is given a certain prior distribution here, which is like a standard Gaussian, and then we try to define a function for y given z. And so, for example, we can define a distribution like this, where z itself is a standard Gaussian, and then y is given by this distribution, which is just an arbitrary function f of z. This function could be linear or nonlinear, and then the standard deviation could still be the like fixed parameter or some sigma parameter. And so this could be this is a generative model technically. The combination of these two lines is a generative model because I can simulate from it. I can easily simulate values for z from this distribution, and then given each value of z, I can simulate the value for y, and then I get samples from y. Now the hope is that, or the goal is that I can find the best function f and the best sigma squared or sigma parameter such that the simulated distribution matches my observed distribution, right? So I have maybe real observations y here or data yi, and I would like to capture this distribution in some way. And so the hope is that I want to be able to simulate from this standard Gaussian, pass it into this function f, which I can train. I can fit this function however I want. First, I can define it however I want, and then I can fit it afterwards. But the hope is that the final distribution of response is going to match the final or the distribution of the data. And we can do this just by checking maybe the histogram of the marginals, just checking the histogram of each dimension. Do they match or not? Or there are other measures that compare distributions that we can also use to guarantee or to confirm that, yes, indeed, we have learned the distribution of the data correctly using this probabilistic model. But how we do that is slightly out of scope for today. Now, once we have this model y given z for a given, again, I said this z is going to be like it's like a latent parameter or latent random variable that's used and passed into this function f. I can actually try to solve the inverse problem as well. And so, given a certain data point yi, I can try to find what is the best z or the most probable z that would predict y. Right. So if I give you a yi, I want to find the best zi that will predict this y by maybe minimizing the sum of square, for example, between y and f of z. So I can take the sum of square between y and f of z, or the log likelihood here, and then optimize with respect to z, and then find me the best z that fits y. And so I can try to solve the inverse problem in this way, and this essentially can be thought of as feature extraction when you solve the inverse problem like this, because let's say z is only one-dimensional or two-dimensional, but y could be 10-dimensional. So I can have 10 numbers in y for each, let's say for each data point is a 10-dimensional point, but I can only have 1 or 2 points or numbers in z. And so if z has a lower dimension than y, then this inverse problem is essentially dimension reduction, or another term is feature extraction or embedding. Now, if z is discrete rather than continuous, and I solve the inverse problem like this, then that's essentially clustering. That's what I said, like with the same probabilistic model, if you like work with it in different ways, you can use it to achieve different tasks. So I can start with a generative model to learn that the task here is just to learn the distribution of the data. But once I learn the distribution of the data, there are various things that I can do. For example, if the latent variable dimension is smaller and I solve the inverse problem, I can also do dimension reduction. If the latent variable is discrete, or at least one of them is discrete, I can use it for clustering, etc. And so the nice thing about probabilistic models is that they can be like they're multi-purpose. They can be used for multiple different tasks. And that's why we try to focus on them and DeepPumas. Now, let's take specific instances of these models. And by the way, I feel free to interrupt me and unmute yourself and ask questions if you have any. And so there are different types of specific models that have names that we can discuss that are basically special cases of what we discussed so far. And so if we look at something called probabilistic principal component analysis, it's very similar to principal component analysis, but it's based on probabilistic modeling. The idea here is Z is still the standard Gaussian in probabilistic PCA, but the difference is that now we have this function f defined as an affine function. So it's an affine function, meaning it's a linear function with so a coefficients matrix A and an intercept B. And again, the dimension of Z here is generally going to be lower than the dimension of Y. So this is the number of principal components that we want to extract, is the dimension of Z. And so if you define your generative model like this, essentially, you can use it to, or it's essentially a model that has a name called probabilistic principal component analysis. And you can fit this model. We haven't discussed yet how you can fit it. But generally speaking, people use the marginal likelihood to fit these models, which is hopefully, again, ringing more bells as to like why I'm claiming that generative models and nonlinear mixed effects modeling are the exact same thing. But the marginal likelihood is often used to fit these models. But then once you fit them, you can actually solve the inverse problem. And so given a new point y, so I can give you a point y with 10 numbers in it, you tell me exactly what are the two most important numbers or features to extract from this. And I can do this again by solving, literally minimizing the sum of square here, or I can also take into account the prior distribution. So I can just sort of do like a map estimation or maximum a posteriori estimation of Z, because Z has a prior distribution given a response Y. Again, hopefully you start to think, okay, this is very similar to the empirical Bayes estimates that we do in pharmacometrics, because it's the exact same thing. It's the empirical Bayes estimates. And so essentially the features here are, or if you can think of the empirical Bayes estimates of a PKPD model as the features extracted from your time series data. So you have this complex data that's time series, and your empirical Bayes estimates are essentially features extracted from this complex data. But Z here can be fitted, again, in the same way, or you can solve the inverse problem given Y. I can try to find what's the best Z that gives me the best prediction for Y. Now, another example where if instead of using a linear function here, if I use a neural network, and actually you would also commonly use a neural network for sigma as well. But here you would get something called a variational autoencoder, or at least this would be called this would be the decoder part of the model. This combined with, this is a neural network here would be considered the decoder part of the model. And again, more commonly, you would probably have a neural network for the sigma square as well as a function of Z. And so variation autoencoders, they revolutionized generative machine learning maybe more than 10 years ago, and they're still very, very useful and relevant today. A lot of models can actually be rewritten as variation autoencoders. There's a lot of good theory behind it. Now, we're only discussing the decoder component here, just to again show you the similarity. But often variation autoencoders are fitted in a slightly different way. You still want to maximize the marginal likelihood, but you construct a different approximation, or rather lower bound of the marginal likelihood, and then you try to maximize that. So I'm not too interested right now in the fitting details of how we fit these models, but rather in just the general idea that this is the decoder part of the model, or this is the generative part of the model. This is how I can simulate data. If I sample Z from a standard Gaussian, I can simulate or find the output of this neural network. And then if I have also another neural network here, I can find this output of the other neural network, and then I can build a normal distribution with this mean and the standard deviation, and then simulate from it and get samples Y. And so I have a mechanism to simulate from this, which makes it a generative model, essentially. And so, but again, I also have a mechanism to invert this process by going from assuming that we have observed a value for Y, trying to find the best Z that would fit this Y, taking also into account the prior distribution of Z. Now, another very famous model that you may have heard about is called a generative adversarial network. And the generative part of this model, or the generator in this model, is actually very similar to this, except that we take out the normal distribution. And so instead of a normal distribution here that we're assuming, we just take the output of the neural network directly as the sample. So I can still sample values from this because the Z, it's a standard Gaussian, and I can just evaluate the neural network, but then the final sample Y is just the output of the neural network directly. We don't go through this another Gaussian error model at the top. Now, this makes it harder to train because the log likelihood now is a lot harder to compute, and it's not tractable. And so people use something called adversarial learning to fit these. But otherwise, it's a very similar conceptually to a variation autoencoder, except for the way that it's trained, and except for the fact that we don't have this normal distribution at the top, right? But again, hopefully you see how all these different models are sort of special cases or slight modifications of the basic structure that we discussed here, right? This basic structure that we discussed earlier. And as I said, if your latent variable is categorical, then this is clustering, essentially. So you can have a categorical prior distribution with some parameters phi, one parameter for each category. And then I can, have a different mu or mean for each category, a different sigma for each category. And so this is just a simple clustering algorithm with a mixture of Gaussians. This is a mixture of Gaussian algorithm, or a mixture of Gaussian distribution, right? Where I have some categorical distribution that's a latent variable. And then based on that category, which could be, let's say, 1, 2, 3, or 4, I have a different mean and a different sigma. All of these are parameters that we can fit simultaneously with the goal of maximizing the marginal likelihood, or learning the distribution of the data. So again, hopefully you see that this probabilistic modeling approach allows us not just to do multiple tasks, but to unify much of the theory of nonlinear mixed effects modeling and pharmacometrics and statistical modeling and like Bayesian statistics, etc., with the theory of machine learning and what people are currently doing. Like these are all state-of-the-art models, or at least they used to be state-of-the-art a few years ago. And so like generative adversarial networks and variation autoencoders are still relevant models today in machine learning, and it's not like they're not very old or forgotten models. Good. So given the time, I'm going to keep today to a theoretical discussion because we don't have that much time left. And so I'm going to skip a lot of these slides and go to the end to hopefully, again, explain or showcase why we think this generative modeling and nonlinear mixed effects modeling are very similar to each other. So I'm going to start introducing conditional generative models. So we've seen a whole bunch of generative models. Now let's see how we can bring in the conditional part. So the only difference really is with the conditional part. So first I'm rewriting the general structure of the model that I had earlier. So I had this Z, which is the latent variable that was defined. It was like a standard Gaussian. Here it's Z. And then before I had Y was normally distributed with mean F of Z and some standard deviation or variances sigma square. Here I'm just defining epsilon first as a normal distributed residual, essentially. So this is the residual from the prediction. And it's normally distributed with mean 0 and variance sigma square. And I'm defining Y or generated Y, which is YG here, just changing notations a bit, as F of Z plus epsilon. So how do we sample from this? We sample a value for Z, we sample a value for Y, for epsilon, and then we can So this would need to be, for example, identity here. So I would need to have, so epsilon I means that every component of epsilon is actually a vector, and every component of epsilon is normally distributed. So these are all independent components of epsilon. Okay, but the way to sample from this is we sample from this multivariate normal, standard normal, and then sample each value of epsilon for each value of I, and then evaluate f of z and add to it the vector epsilon to get the y. Okay, but otherwise this is the exact same model structure that we had earlier. Now, what is the objective here? The objective is to find the best function f such that the distribution of yg is as close as possible to the distribution of the observed data. So we start from this generative model idea. Now, how do we make it conditional? We make it conditional just by adding covariates here. So now we have not just the latent variable z, but we also have this covariates x. And so once you have a covariate x, you can now, for each set of covariates, you can learn a different distribution. So I can fix x and still be able to simulate values for yg. So I can fix x, for example, male or female, and then still be able to simulate values for z from normal distribution here, and then values for epsilon from this normal distribution, and then evaluate f of z and x, add it to epsilon, and get a whole bunch of different generated or synthetic values for yg for a specific value of x. And so that's why it's often called a conditional generative model. Now you can think of yg as just a vector of numbers, like in probabilistic PCA, for example, or principal component analysis, or you can think of yg as an image, or you can think of yg as a time series. So you can think of yg as anything. It could be any kind of distribution at the end, as long as you have this function that maps from z and maps from the covariates to essentially y, or to a prediction of y. Now, this should all look very familiar because now I did just one simple change, which is replace z by eta for the latent variable, and then replace the distribution here from being standard Gaussian to being a distribution with mean 0 and covariance matrix omega. And then epsilon stays the same. It has sigma square variance. And then f of theta here is our PK model, for example, that goes from the random effects and goes from the covariates and then simulates or predicts the concentration of drug at specific time points. So let's say all the subjects for simplicity, all the subjects have the same time points. And so we can easily see how a PK model would essentially fit this same template just by changing some notation, right? And changing a few things. And when you think about what's the goal of a visual predictive check in pharmacometrics, it's actually the exact goal that we set out here at the beginning, which is to choose the function or the best function f of theta, or the best population parameters theta, such that the conditional distribution of our response, the concentration of the drug given the covariate for each set of covariates, is as close as possible to the conditional distribution of the observed data, the observed concentrations given the covariates. And so if I have a lot of data for a lot of different types of covariates, the goal is to be able to look at the distribution, maybe look at the covariate on the x-axis, for example, time, or some other covariate, and look at the distribution of the response, the observed response, and then the simulated response, and seeing, are they matching or are they not matching? If they are, then we've learned a good generative model, which also means we've learned a good nonlinear mixed effects model, or PKPD model. And that's what I mean by saying they're the exact same thing, because the goal is the same, the structure is largely the same. The only difference is how we train them and how we define this f of theta. But the objective at the end is the same, and the structure is more or less the same, the overall mathematical structure. The difference, again, as I said, is that the function f will be different. In much of the modeling that we do in pharmacometrics, f of theta is going to be mechanistic. And so you can define your PK model, your PD model, etc., or it could be semi-empirical in some ways. Another difference is that the random effects often have an interpretation in pharmacometrics or in nonlinear mixed effects modeling. For example, it can have the interpretation of the deviation from the typical value. So theta will have some interpretation. It will be interpretable. We assign a certain meaning to theta. We assign a certain meaning to eta, or to the random effects, where the random effects here can be, again, deviation from typical clearance, deviation from typical volume of distribution, etc. And the covariate model is something that we also define ourselves explicitly. And so all of this structural knowledge or scientific modeling or scientific knowledge is encoded into this function f. But otherwise, if you look at the overall structure, it's almost the exact same as the structure of these very traditional, very classical machine learning models that people have been using for years. What's interesting is that the people from both domains actually, there's very little overlap. And so looking at both fields, it almost feels like some of the same concepts are used in both fields, but they have different names or slightly different details associated with them. And I think once you have this unified view between both fields, you start seeing a lot of different things that you can learn from machine learning and bring over to pharmacometrics and vice versa. And you also don't have this sort of like conceptual war in your head going on between should I use machine learning or should I use PKPD or nonlinear mixed effects modeling, because they're really both the like trying to do the same thing at the end of the day. And depending on how much machine learning you build into F versus how much scientific modeling you build into F, you can be in different parts of the spectrum of machine learning versus scientific modeling or anywhere in between. And DeepPumas is just a software tool to allow you to explore this whole spectrum with a lot of ease. So you can define your machine learning models, your pure machine learning models that are also hierarchical in nature. You can define your pure scientific models, and you can define everything in between. Any questions?
Maybe just a very naive question, but the theta here, like f of theta, is it the same theta we used in non-mem, or there is something?
Yes, it is. So theta here, for example, in a let's go back to the warfarin example. So the omega is the same omega here, right? The sigma square is the same sigma square. Okay, this is not the warfarin example. The warfarin example is here. The omegas are essentially all these omegas here, right? The sigma square is in our models, the sigma fx and sigma and all the proportional sigma and the additive sigma. So here I'm assuming an additive error model, but you can also have proportional error models, no problem. But these are all the sigmas, and then everything else is your theta. And so your f of theta is this. So f theta here, or f theta of eta and x, is this CP, and also this turnover, right? So these here are the output of f. And theta is all the parameters that were used to build this output. And so we have the random effects. So x is, what is x? X is the covariance, right? And we have our random effects coming in, all the etas here. So all of these are the etas, this eta here, right? And then theta is all the other parameters. So pop CL, pop V, pop tabs, etc. All these other parameters are the theta, right? Now, much of the knowledge here is encoded into the model itself and into maybe the dynamical system, pop lag, etc. All this lag, the fact that we have those control parameters or lag, the fact that we can initialize turnover from E0, this is all your scientific modeling coming into play, right? Now, technically, I could have removed all this and just use a neural network to go from the random effects straight to the CP. Now, I could have done that. In DeepPumas, you can do that. And maybe use just time as input. So just have time as an input here and just call it a day. But because we have all this scientific knowledge, we try to take advantage of it because that can give us more interpretability and more data efficiency when we're trying to use this model or fit it to data. We don't need as much data anymore. And the models can often still be interpretable. But maybe this function here, for example, maybe this function, we can replace it with a neural network because we don't know for a fact that it's going to be following this Emax function. And so we can just make it a function of CP and maybe some random effect. So let's define a new random effect here. We call it NN eta, and then we can give it a random effect to individualize the output. And then we can give it CP, maybe give it another random effect because here it has Emax. Emax has a random effect and C50 has a random effect. And so instead of this function, I could have defined it as a neural network instead. Right, and that's actually valid DeepPumas code. So it's just I need to define NN now up here somewhere. So NN needs to be defined in the population parameters essentially. So if I define NN here in the population parameter as some multi-layer perceptron, this is pseudocode, so this is not complete code, and you need DeepPumas to run this. This is not going to work in Pumas. But if I define the neural network as a multi-layer perceptron here, or just some maybe 3 layers neural network with any activation function, then I can essentially use it directly here to define my exposure response model instead of relying on Emax. And if I still want to, what do you call it? If I still want to use this asymptotic behavior or have this asymptotic behavior, then I can actually do something like this. So let me just bring back the model. I can replace CP here with maybe NN equals this, and then this NN now comes into the place of CP, right? So I can still, and then this can be like population parameters or something like that. And so the NN can still have the same sort of behavior as an asymptotic behavior, but also I can learn maybe a more complicated function of CP than just a linear function. Right. So instead of using CP here, I can use the neural network. And so you can see there's a lot more flexibility in how you can mix and match scientific modeling or assumptions with a use of a neural network. But you don't lose much because you can still use all of your old tricks essentially here, and you can use all of your old diagnostics. So once you define a model like this, you can fit it with FOCE. You can call the coefficients and get the individual coefficients. You can call you can find the empirical Bayes estimates, get the visual predictive check. So you have access to the entire pharmacometrics toolbox, but at the same time, you can use machine learning directly inside of your model, and not to replace the whole thing, but just to replace one small component of the model that you feel like you need to replace. That was a long answer to maybe a small question, but I hope that answered your question.
Thank you. It was very helpful.
Any other questions?
Yes, I hope now you can hear me.
I can, yes.
Wow, yeah. Okay, thank you. So if you are using, that was very nice also to demonstrate here. So if we stick there to the line 139, that you have this component of neural network now in your entire framework, what is actually the output then of that?
Yes, the output can be whatever you want it to be. In this case, it could be a single, like a vector of length 1. So in this case, I'm interested only in a single output, right? This is, I'm interested only in a single number here. And so I can only define it to have, like, I can define this to be, for example, a neural network with 3 inputs, and then maybe as many hidden layers as I want. So I can maybe give it 5 hidden layers and an output layer with 1 output. And so I can define the architecture of the neural network in this part here in the MLP domain, right? So this is where you define the architecture of the neural network here. And then the neural network is just fitted like any other population parameter. So the weights of the neural network, the parameters of the neural network are fitted like these other population parameters. But again, in this case, it makes sense to only have 1 output because I want to replace CP here. And so I'm going to have just a single output here. But I have 3 inputs because one of them is CP and 2 other random effects. If I want, I can remove 1 random effect, and then it only has 2 inputs. So you can really do whatever you want. That's sort of the idea. And if you want multiple outputs, you can have multiple outputs as well. So for example, if I want to define a neural ODE, I can define here like all the rates of change, for example, rates of change, and then define this as another neural network, right? That takes in things like depot, and then takes in things like central, takes in turnover, right? So all the 3 compartments, so maybe it takes a bunch of random effects, and then this here can just be used directly as the rate of change of the first compartment, right? So the first element of this can be the rate of change of the first compartment, then the rate of change of the second, rate of change of the third. Now this is not a good idea because now I'm throwing away all this knowledge that I had built into the model, and now I'm just relying on a neural network to learn all of the dynamics, which is going to work. This kind of model is often called a neural ODE. It's going to work, but it's not going to be the most data efficient because I'm throwing away a lot of the information. And I can define the neural network NN2 now to have 3 outputs instead of just 1, right? Because it makes sense in this case. Does that make sense? Does that answer your question?
No. Yes. No.
Yeah. And the 3 outputs are all accessed here in separate places. But of course, again, this is not what we recommend. This is against the spirit of scientific machine learning because we're losing a lot of information. And so if you want, you can, for example, maybe have this rate n be a neural network, but then use the same, like this could be some neural network function, but then use this same rate n or the same function here down there. And so that at least we have the knowledge that all the drug that comes out of VPO goes exactly into central. Right, so this is scientific knowledge that will take a machine learning model many points to learn, but you already know that this happens, and so you can encode this directly by just having the exact same function used twice, or having this like saving it to a variable here and then using it twice, right? And so you can replace your components of your model, like surgically replace components of your model with machine learning where you think it makes sense, and only do it one step at a time, testing that there's actually an improvement. So you don't just replace the whole thing. You always make sure that there is an improvement as you replace one part at a time. And then once you confirm that, yes, there is a noticeable improvement in the IPRIDs, in the VPCs, in the log likelihoods, in the residuals, etc., then you can go and try something else. And so we promote, or we always encourage this stepwise approach, where you start from an existing model that you have that works well for many cases, but maybe not for this new data set, which might be novel in some new way. Maybe the drug is different in some new way. And then you can start experimenting with different parts here, where you can add a neural network maybe to the absorption, or you can add a neural network to the clearance, or you can add a neural network to the sort of the exposure response model, or in any other place. Right? Or if you suspect you have mixture models or like multi-modalities in your random effects, then you can transform the random effects here with a neural network. So I can define another sort of like, let's say, transformed eta here, and then this could be another neural network of, let's say, PK eta. Right. So I can use a neural network here and transform this, and this allows me to learn more multimodal distributions of random effects, even though I start from a Gaussian here. But the output of the neural network can allow me to learn, or using a neural network here allows me to learn some nonlinearly distributed random effects, or even multimodal distributed random effects. And so the sky is really your limit, and you can use neural networks everywhere in the Pumas model, which again allows you to improve it in various ways. And the question is, how do you want to improve it, or where do you suspect is the most potential for improving these models?
Yeah, thank you for this extensive answer. The question also is, can you also further explore the neural network?
Yes. You mean at the end, once we fit it? So yes, we can take a look at it. So because the neural network is defined here in the population parameters, actually, once you have a fit, so let's say we already called the fit here, if you use coef on the fit, you will get the neural network, and then you can actually get the neural network out. And this will be the fitted neural network. And because it's fitted, you can now take it and actually like assign it to a variable f. And now I can take a look at like call it for different inputs. So I can call it for a whole bunch of different inputs, for example, -10, 0.1, 10, and then I can plot this and see what it looks like. And if it's just a single input, it's easy. If it's multiple outputs, I can use other sensitivity analysis methods and try to figure out what exactly is this function trying to tell me, and make sense of it. So yes, because you can easily sort of inspect the fitted neural networks here. You can even get, if you have like random effects, you can get the empirical Bayes estimates and also pass them as an input here. And so see, for example, for some values of the empirical Bayes estimates, you can call the empirical Bayes function here, and this will give you all the empirical Bayes estimates of the random effects, including the ones that were input to the neural network, and you can try to use them directly as input here and plot this. And so all of the machinery of Pumas that we have seen in this workshop can basically be used directly even in neural network-based models. And that's why it's a prerequisite in order to learn DeepPumas, you have to first learn Pumas and know some Julia, because it allows you to take the full advantage of DeepPumas.
Thanks.
Any other questions? Now, I kind of had to rush this whole DeepPumas session here. We only had 2 hours. Usually we have a lot more in Page and ACOP. We spent some time discussing Pumas and Julia, and so but 2 hours is definitely not enough if you want to get a deeper understanding. And so if you're going to be in Page, I recommend you check out the Page DeepPumas workshop, which I believe is not yet on the Page website, but it should be up soon. So maybe just stay tuned, and it will be there. If you're available again in April before Page, and you would like to come for the Basel workshop in Switzerland, we will be doing a 5-day workshop there as well that covers a lot more material than what we covered here. A lot of the material is also prepared by my colleague Lucas Pereira, who's with us here as well on this call. Yeah, we have a lot more exciting stuff coming up this year in terms of education and training. So stay tuned, and any more questions? I don't think I have time to discuss anything else today, so this is probably it from my side. So the rest of the last 15 minutes, I'll just be receiving questions, and if you are okay with it, we can also take a group photo and maybe spend a few minutes filling up the form that I sent you earlier. But yeah, let's do let's do the question answering and the form filling simultaneously. So if you're not asking a question, please open the form and try to fill it up. But if you have any questions, please unmute yourself.
I have a very, yeah, it may sound a little too funny, but what is a neural network?
Great question. So a neural network is the part that I skipped essentially here because of the lack of time. So a neural network is nothing but essentially a nested function. It's a hierarchical function. Actually, it might be easier to just show you. Let's build a neural network right now. So let's say I have let's say I have 2 inputs. I want to build a neural network with 2 inputs with 3 hidden layers, and then with let's say 5 outputs or 6 outputs. It came out like this. And then there's something called an activation function. And so an activation function is just a nonlinear function that's used to build a neural network. So let's say we're going to use the function hyperbolic tan. It's a common choice. And so a neural network is literally nothing but a function of a function of a function of a function. So it's like a nested function. And so the way we're going to do this is we're going to first define a whole bunch of coefficients or weights. So let's define the first weight here, which is going to be some random matrix. So we're going to start from random weights, and it's going to be a 3 by 2 random weight. And then let's say that there's 3 hidden layers, but each hidden layer has something called 10 neurons or neurons in there. And so the first weight is going to be like this, and then the first bias is going to be a vector of length 10. And then I'm going to define a couple more weights here and a couple more biases. And this one will be a 10 by 10, and this one will be 10 by 10. And then I did say 3 hidden layers, let's make them 2. And then 1 output layer with 6 outputs. Okay, so for the output layer, I'm gonna define also another weight like this, and so it's a 6 by 10, and then B4 is a vector of length 6. So these are all just a bunch of parameters. So it's lots of parameters, right? It's like there's 20 parameters here, there's 10 parameters here, there's 100 parameters here, and so it's a lot of parameters. How we're going to put them together is the interesting part. And so if I want, first I start from let's say tan h, which is the activation function, and then let's define a function f1 of x, and this function f1 of x is nothing but tan h called element-wise on W1 times X plus B1. So this is called a layer in a neural network. It's nothing but you have an input X, and then you have the weights W1 that you multiply. So this is a weight matrix, you multiply by X. And here this has a shape of 10 by 2. This is a matrix that's 10 by 2, and the number of inputs is 2. So we're assuming here the number of inputs, X is 2-dimensional. Okay, and so what we get here is a vector of length 10, and then we add to it B1, which has again dimension 10, right? And so we get another vector here of length 10, and then we call this activation function, or this nonlinear function, on each element of this output, and that's the output of our first layer. And then the second layer is very similar, but now it's W2 and X and B2. And the third layer, and here now X is going to be 10-dimensional. So X is coming in from the previous layer. Okay, and so X is the output of the previous layer. And then here, F3 is nothing but the exact same function structure, but with W3 and B3. And then for the final, we have F4, and this one will be using W4 and B4, and this one produces 6 outputs, or 6 numbers, right? So this returns 6 numbers, or a vector of length 6. Just because the size of W4 here was a 6 by 10 matrix, and the size of B4 is a vector of length 6, right? And so the neural network is nothing but f of 4, of f of 3, of f of 2, of f of 1, of x. That's a neural network. Or that's the simplest neural network, right? But now you can think of all sorts of crazy ways to nest these functions. But the building block of a neural network is called a layer, and a layer is nothing but a linear transformation like this, followed by a nonlinearity or some nonlinear function like hyperbolic tan. Now you can then go a bit crazy with this. So maybe you don't want the last layer, you don't want any activation function. You want this to be unconstrained. Maybe you want this to be between 0 and 1, so you can call something called the sigmoid function. So you can get creative with the nonlinearity here, and you can get creative with even the linear function here. Maybe you don't want to use all of x and you want to have like a special there's something called a convolution layer, for example, that doesn't use all of x, but uses only like tries to extract features in a more clever way. It's not like just a dense layer, but so this is often called a dense layer. So this is the very simplest kind of neural network that people use, and we use this a lot in DeepPumas. Now in DeepPumas, we have a very simple way to define this multi-layer perceptron. This is called a multi-layer perceptron. This is often called a perceptron for some reason. And then when you have multiple layers of them, this is called a multi-layer perceptron. But again, at the core of it, a neural network is nothing but an extremely over-parameterized function. Lots of parameters, right? And then nesting of these functions on top of each other. And the end result is a function that's extremely flexible. I can try to train all these weights and biases and get something that looks like my data. And so that's what a neural network is, or at least that's the simplest kind of neural network. Does that answer your question?
Yeah, thank you. It helps.
All right. Okay. Any other questions?
Maybe one short question. Do you have any experience with DeepPumas and regulatory interactions? I mean, it's still an early product, right? And you're still playing around with it. I'm just wondering what the regulatory agencies are saying to that.
So if you're asking if any submission was made to DeepPumas, the answer is no. But we have been talking to regulatory agencies, and at least the FDA, for example, in the US, we have some contacts there, and they are open to these new techniques and using machine learning in different ways. So far, I don't think I don't think everybody is clear yet on exactly what can be done. But the problem is that I think that usually companies tend to be more conservative than regulatory agencies, especially in the US, where if you ask the FDA, why do you think machine learning has not been used that much in submissions? They'll tell you that we're open to it. We have guidelines and people can try. But then if you ask companies, why aren't you trying to submit with machine learning? They'll tell you that we're worried about the FDA not accepting it or something like that. And so there's always this someone needs to take the first step and try it out. But it seems like there's interest from everybody, but I think the interest has not yet been sufficiently, let's say, instantiated and demonstrated and resulted in real submissions and real approvals. At least to my knowledge, there aren't that many submissions out there that have yet used sort of this whole idea of combining machine learning with scientific modeling. But that said, you can still use this technique for maybe internal decision making. You could use it for dose selection, for example, if you're trying to plan a clinical trial. You can use it for exploratory analysis to see, is there any point in doing scientific modeling or not? So you can start by doing this kind of modeling. It's very easy to do in terms of it doesn't need many hours from a scientist to try to figure out this. And so you can throw all your data in there and see what comes out. And then if something comes out, you can now look at the functional form and try to guess it and try to come up with a more scientific model or develop hypothesis. So you can use this for hypothesis generation, testing. Are any of the biomarkers even useful or helpful? So you can throw all the biomarkers in there, and if it tells you, yes, these 2 biomarkers might be helpful, you try to look further into that and generate hypotheses and so on. And so even though it might not have been used yet in a full submission, but there are so many other steps before that where you could utilize this tool and where it has been utilized for internal decision-making, model development, hypothesis generation, etc.
Okay, makes sense. Thanks for sharing.
Okay, so I think we're nearing the end. So thanks, everyone. And I hope you enjoyed this long 12-hour workshop of ours. Yeah, and if you have any questions afterwards, or if you would like to explore more of these ideas, please feel free to contact us. We're actually a friendly bunch, and we enjoy talking about ideas and research. And so, yeah, if you have any ideas that you would like to explore, then feel free to reach out, and we can hopefully help in some way. But otherwise, thank you all for your attention.
Thanks a lot, really, Mohammed. Maybe I have a question. You said that you have also, for example, a satellite meeting at the page. Is there also any workshop or any event that you offer that there's also some hands-on exercises that you include?
Yes. So in that workshop, there's actually also exercises. I haven't had the chance to show you all the exercises because we only had a couple of hours. But yes, there is a lot more exercises in these workshops in general, whether it's the one in Page or the one in Basel, which we would have. So the plan for the Basel workshop, because it's 5 days, is to have a full day where you come up with your own project essentially, and we can give you some candidate projects that you can try, but otherwise you can bring your own data set, your own model, and explore. But yes, there tends to be a lot more hands-on in these workshops. So whether it's the Page one, which is only 2 days, or maybe a day and a half even, or the Basel one, which is going to be 5 days.
The announcement at the Page website then will come very soon. No.
I hope so. Yes, yes.
Yeah. It's already on your website announced.
It's already there?
Yeah, I just checked.
Awesome.
Okay. Good, Rinka.
Okay. So I guess everyone, and yeah, I guess I'll see you around in conferences and maybe other training. Thank you.